Alright, hell yeah. So we have physics for scientists and engineers. And man, this is a baseball problem. And this one stumped me. We're actually going to go over the problem in just this one page. You know what I mean? So if you stick around for that, probably, 4 to 5 minutes, we'll be there. So what we're going to do on this is just kind of explain what's going on. We have a baseball player that usually just throws from the outfield just one big arc and then lands and then maybe tries to get someone out. But they say that if you lower your angle, you know what I mean, you can get there faster. The situation happens, though, that if the ball does bounce, it loses half its speed. You know what I mean? So we're going to say the baseball player can throw with the same velocity no matter what angle. But we're going to show that this goes faster. You know what I mean? And so that's cool. The same distance, you can get there with one hop, and it's going to be faster. Okay, so in this problem, it was a conundrum for me. So the straight up process to get there is that you have acceleration of gravity trying to slow the upward velocity. So this has two components, and I guess I will write this in. So you have a v initial cosine theta, and then you have a v initial sine theta, the vertical component. Anyway. So if we integrate the acceleration, and I'll go over that in the next page, but if we just follow this, it goes from 9.8 to negative 9.8 t, plus a constant though, once we integrate. So when t is 0, the initial velocity is straight up v initial sine theta initial. Theta initial for this problem is the 45-degree angle, and then moving on. We integrate again to get position. Negative 9.8 t squared, and hell yeah, we got some errors going on here. This should be divided by 2. Apologize about that. Holy Toledo. That's going to be crazy. Hopefully, I'm just copy pasting from what I did before. Okay, so oh, you know what? I made an error through this whole video. This whole video, I did not do square root of 2, but it wasn't even a function of acceleration. None of this was a function. I have to go back and then look at everything now. Because, so even all these terms with 9.8 should be divided by 4.5. But they're all out in the wash, and that's so fascinating because the actual, holy Toledo. Okay, so this is a learning moment, you know what I mean? Because even after I did it, just like, oh, so perfecto, the actual equation has no parameters of acceleration in it. So if you can bear with that one mistake, such a learning process. We're going to forge through. Everywhere where you see 9.8, it should be probably 4.9. You know what I mean? 9.8 divided by 2. Okay, so we integrate to get the position equation, and then you get this for position. Now, if you wanted to find the time that it actually hit the ground again, this says, hey, if you throw in 0 here, you know what I mean? Well, what's the time? Well, obviously, time is 0, but you can, for the next part, we're going to show how, you know what I mean? Hey, factor out a t, and then you can figure out that the time of when it hits over here is v initial sine theta initial divided by 9.8. And again, holy hell, it should be 4.9, I think. Everywhere where it says 9.8, oh, this is wicked. I apologize, but let's forge ahead. So that's going to be for that one arc. We have velocity and position. Cool. Let's do it for these smaller arcs. Well, this smaller arc is the same as the first one. Except we just don't know the angle. So, well, let's take a pause. And so we also know the acceleration in the x direction. So we're still on the first arc at screen. And so we can integrate and get just the constant. When you integrate 0, you just get the constant. And so we're saying at time 0, you know what I mean, what is... Because, yeah, that's a cool thing. You know what I mean? This is never mind. But at the initial time, we have velocity initial cosine theta. Theta initial is 45 for this problem. So theta initial is 45 degrees. Theta prime is the angle that we want to throw it to do the 2 hops. So cool, we got some more equations, we got the velocity, and now we can get position in the x. So as this direction as a function of that time. This is 45 degrees. Cool, and now we can do that same process for this blue arc. I'm going to call this blue arc prime. So this is prime, this is double prime. So the time it takes is t prime there and t double prime there. This green arc is just t. So we solve for t for that one. We get our equation for the velocity. It's going to be the same. The only thing that's different is this velocity double prime in the y. Now, when it hits the ground, it's going to just be half of this initial velocity. So for this problem, I'm going to run k through here, and I'm going to say k is just 1/2. You know what I mean? So then, at the end of my problem, I have an equation as a function of k. Because let's say I do some experiments, throw some balls in some grass, and maybe some grass it slows it half, and some grass it doesn't. Or if it hits dirt, maybe it only slows it like 60%. So I can adjust that k value, and maybe that's going to adjust my angle. You know what I mean? To really tweak this one out. Okay, hell yeah. So we have that equation for the velocity in the y. Same process, I get the equation in this. And it's pretty much identical, except we have a different angle. That's the only thing. Theta naught is 45. Theta prime is what we want to figure out that angle for the 2-hop. But now we go to this one. The velocity is different. We have that k. So then the position is different. We have, it's again a function of k. All right, hell yeah. So for this one, we can figure out the time, you know what I mean? So now we have k v initial sine theta, and I apologize. Everywhere where it says 9.8, it's so funny, but this equation is not a function. I'm going to say it again, not a function of acceleration. And so, you know what I mean? This error did not show up in my calculations whatsoever. That's embarrassing, though. Okay, so once you get to there, you have to figure out what the hell is going on and how to solve the problem. You know what I mean? Basically, we're going to say there's a continuity. I'm gonna say this distance is A and this distance is B. That made all the you know, that really helped, because now what is distance D? Well, from this green arc, it's just, let's say this component of the velocity, that's unchanging. So it's just this component times the time it actually took to do that. Well, we solve for the time because we solve the quadratic. And we get these times for the green arc, this first arc, and then the second hop. And so if we know those times and we know that the velocity is constant, so now we go over here. The velocity of x is just v, for the green, it's just v initial cosine 45. The velocity of this arc in the x is v initial times the cosine of the angle we're trying to find. And the velocity of this in the x direction of this one, well, it's going to be that factor of half. So if we say k is a half, it's going to be 1/2 velocity initial cosine, and I'm sorry, we're on this velocity. 1/2 velocity initial cosine of the angle. And we're saying that the other thing that's fascinating with this problem is they're saying that when you throw at this double bounce angle, once it, and this makes sense. This is like pool balls. You throw it up and then it comes down. It's going to hit at the same angle. So that means like a pool ball, it's going to bounce at the same angle on the next bounce. So cool. All right, we got that. So now, yeah, so we can find these distances. Distance is just the time, or the other way to do it is like, well, we already have an equation for this distance. This equation A is literally, we solved it. It's the position equation x. You know, throw in t, so hell yeah, so here's our t. So we throw in t into the position equation, that is A. So, and then let's do B. So we have the position equation of this second ball. It's x double prime, and so we're going to have k v initial cosine naught of the and then time 2 is this. You know what I mean? So if I plug in t double prime. So if I throw in t double prime there, I get b. So that's what we do. D is equal to a plus b. A is going to be See, the v cosine evaluated at t, so there's that, is equal to a, which is v cosine theta with t prime. So I throw in t prime right in there and get that. And then I have b is position equation here at evaluated at t double prime. Throw that in there. Hell yeah. So now I have d is equal to a plus b. All the VI's cancel. There's the VI squared, so there's 2 VI's there in all of these. There's the 9.8 in all of them, which should be 4.9. My huge apologies. That's crazy. But those all cancel. And then so at the end of the day, look, you just have cosine of that 45, sine 45, which we're calling theta naught, is equal to, now these two can add together. There's a 1 plus k. So no, there's 2 k's. So it's 1 plus k squared. 1 plus k squared cosine of the angle we're trying to find. This side we know, this side we don't know. We use trigonomic identity that says, hey, if we know sine and cosine, sine squared times cosine squared, that's kind of what we have, just reversed. But 2 times that is equal to sine 2 theta. Well, I only have 1 times that, so I'm just going to say it's times a half sine 2 theta. And now we're in, because now I'm going to put that half sine 2 theta, what we're trying to find, and then this is half sine 2 theta of 45. Cool. And now this is what we're trying to find, so we can factor out the half, get this the hell downstairs, and then we have this. And then we're so close. All we have to do is just take the inverse sine of this, which we did right there, and then divide by 2. So hell yeah, there we go. And then the second part of this, it says determine the ratio of times for 1 bounce and no bounce throws. Which all they're saying is just like, hey, like how much, like what's, if this took a certain amount of time, divide it by this longer time. So it's going to be t1 plus, t prime plus t double prime, which we found, divided by t. So look at this. These all have the same things, and that's where my error of 9.8 is just super glaring. But that's it. You know, I'm trying to make polished videos right at the beginning, and we catch such a cool error. But anyway, when you add these and divide by them, all the things that are the same cancel. So those cancel, these cancel. So now you're just going to have, in the top, these both are a function of sine theta prime. And so you're going to have sine theta prime, but this is 1 plus k. So we got 1 plus k sine theta prime divided by that sine theta initial. And there you go. There's the time difference. And now you have the 2 equations, and you can do whatever you want with this. What this says is I'm going to throw at an angle of 45, and when it hits the dirt, this is going to be 0.5. It's going to go half the velocity. And I want to know what angle that gets me there in 1 bounce, the same distance. You know what I mean? 2 perfect hops. Or this would be called a 1 hop in baseball. And then just as a bonus, I can figure out, well, it's going to get there faster for sure, but how much faster? This is, and in the back of the book, this answer was like 0.9, 0.95 pretty much. So it's fascinating that it's from this problem scenario, it's like it's faster. You know what I mean? And maybe that fraction of a second is going to get you more outs, going to win you a pennant or whatever they call it these days. So yeah, so that's cool. So we have these functions. The other thing is we can throw at any angle. I could throw, let's say I'm throwing at a 30-degree angle to get to this point. Well, this says, well, you could do a 2-hopper faster. So no matter what your angle is, there's always an angle lower with a 2 hop. I'm going to call it 2 hop. I'm not going to call it a 1 hopper. Well, with 2 hops, that will get you there faster. And this is the equation for that. First, you have to figure out what surface you're playing on. And with this K, hell yeah, now you can do some scenarios where you can figure out, like, if it's dirt, if it's going to be less than a half, you know what I mean? Or, if it's going to be faster, maybe it's just 3/4, 60%. So you can vary that, and you can vary this initial angle. Okay, hell yeah. So I'm going to go over it one more time because we have like a 5-hour video in front of us, but I'm just going to go over it just with 2 pages, a little bit slower, and then I'm going to start the slog of like this problem kicked my butt, and I'm going to show you the learning process. I took it to Excel. I learned a lot. But it's a slow process. But I take you through that if that's what you want. All right, hell yeah. So now we're going to slow it down just a little bit and learn some stuff. So the first two equations you need are acceleration. The definition of acceleration is change in velocity, change in time. Watch the longer portion of this video. Is just like, I hate dv dt, but I'm used to it. You know what I mean? I like to do acceleration is change in velocity, change in time. That just makes so much more sense to me. And sorry for using such a bum pen. So now this other one, same thing. Velocity is change in position, change in time. Now these literally, in Excel, these are equations. You know what I mean? If we're going to take a small chunk of time, it's going to give us a small chunk of change in x. You know what I mean? So these are legit equations. But when we use calculus, you know, we throw in negative 9.8 as our acceleration. And then so when we get right here, you know what I mean, we have acceleration as negative 9.8. Well, let's put this part of the equation into right there. So now we have dv dt. That basically says acceleration. You don't need to see the a, you can just see this. And if you're super pro, you're able to see, hey, this is just the derivative. Well, it's also the derivative of x dot divided by, oh, and are all my pens going to run out? You know, it's the derivative of x dot divided by dt, and, oh, shoot, I don't even know if I can do, no, we're not going to go there. But anyway, so now you have this in a derivative form. And we know that over here, this is a function of t to the 0. It's a function of x to the 0. It's just not a function of them. But when we go to separate variables, this is t to the 0. And when we integrate, we get t to the 0 plus 1 divided by 0 plus 1. So this it's kind of interesting. That always blew my mind that you could be like, what? We're just integrating a constant? After you do so much complex calculus, you're just like, what? You know, even just integrating a constant seems like actually a difficult thing to do. Okay, so hell yeah. So now we separate terms. We got the dt over there, the dv over here. So now there we go. We can integrate dv 9.8 dt, and this should be negative 9.8. And then we get negative 9.8 there. And this is crazy. At no point today did I ever integrate correctly. You know what I mean? When I integrated a second time, I just said it was 9.8. That's insane. And there was plenty of times, I mean, no, like, just when I polish this video, during the video, I do the integration correct, and I say if I integrate a second time, like integration of t dt, I'm going to say this is t to the 1, I'm going to go t to the 1 plus 1 divided by 1 plus 1. This is t to the 2 divided by 2. I would have caught that error, but in my polished video, I just totally glanced it. So hell yeah. So we have this integration of dv, negative 9.8 dt. So we get equation for velocity is v is negative 9.8 t plus a constant though. And what this says is like, hey, when we throw in time t, what's velocity? And I probably didn't do a very good job here because you have to choose a direction. This is a in the y, a in the y. You know what I mean? If you're, yeah, so that is important. So this is velocity in the y. So when we go throw in t is equal to 0, we want to know what the velocity in the y is. Well, that's v initial sine theta. Cool. So that's why we get this equation. Negative 9.8t plus v initial sine theta. And, yeah, all these are negative. Holy Toledo. Sorry about that. There you go. So you get this equation, and now you do the same thing. Well, actually, I took a pause, and then I said, well, hey, let's figure out the acceleration in the x direction. So we have dv dt is equal to 0, because we just said that acceleration is dv dt. Cool. Throw that in on that side. That's that side. And now we can separate variables. Now, this is even trickier. Integrating, well, how do you integrate 0? And I even messed it up, because we have dv on this side, and then we have 0 times dt. When I bring the dt over here, it's 0 times dt. And now when I integrate, you know what I mean? Sure. I have 0 to the t to the 0. I still have t to the 0, x to the 0. You know what I mean? So even just like 0 is still a constant It's just a zero, a zero constant at the zero level. And then so when I do integrate this, integrate 0 t to the 0, let's do that, t to the 0 dt, sure, I can still go t to the 0 plus 1 divided by 0 plus 1. That's the integration, but guess what? It's still times 0. That constant doesn't change. This value doesn't change. So now I do have t to the 1 times 0 plus a constant. Well, that just goes to 0. But it's just like that's the cool. I love that. You know what I mean? Where you're just like, I would have never done it that way. You know what I mean? And don't just hand wave 0 goes to a constant. You know what I mean? So that's pretty cool. And now at time is equal to 0, because we still have t here. Now we have t to the 1, so I can throw in time is equal to 0, and that makes sense now. And then I can be like, well, what's the velocity in the x? Well, it's just it's a constant, and it's vi cosine theta. Cool. So now I have velocity of x is just vi cosine theta. All right, hell yeah. And obviously, what we do is we no, it looks like we got to do one more. So now we want the second derivatives. You know what I mean? We take the velocity in the y, and we say it's equal to dx dt. Same thing. So now we have dx dt, or it's equal to dy dt. You know what I mean? Depending on what this could be either x or a y right there. So now we're in y. So we're dy dt. Separate variables. We get dy is equal to that dt. Integrate. So now we get an equation for y. And again, this is divided by 2. I totally apologize. Everywhere you see 9.8, just divide by 2. And my bad. I just lucked out on this one again. And then you still have a constant here. Once you integrate, you still have a constant. But guess what? When you throw in t is equal to 0, what's the position in the y? Well, it's right there. You're starting at 0, 0. You're starting at x, y, where x is 0, y is 0. Cool. So when y is 0, at time is equal, and this is time is equal to 0. At 0 time, you're right there, and you're at 0 in the y direction. So this constant is just 0. Hell yeah. And then so you can do that same process for those other two. The only difference is for this second one, your velocity is half the initial. So for a lot of this video, I don't use k. You know what I mean? That was just something cool in the end. But I just do 1/2 v. And everything's the same. But I will, and in the longer video, what I do is like if you have this position, and I'll go over it right now, like when 0 is equal to negative 9.8 divided by 2, obviously, t squared plus v initial sine theta t, like how do you solve for this? You know what I mean? The professional way is to do this. Factor out a t, and now you got negative 9.8 divided by 2 t plus v initial sine theta. Okay, so I just factored out that t. Cool. This is a product of two things. If either one of these things is 0, then it's 0. You know what I mean? So if I have like whatever, you know what I mean, but then it's I think that's straightforward. So one of my solutions is t is equal to 0. I could throw that in. The other solution is if this separate equation, you know what I mean, take it right here, negative 9.8 divided by t plus v initial sine theta is equal to 0. Okay, bring this to the other side. I can just do that by putting the equal sign right there. That makes that positive. And then divide by 9.8. And then there's a 2. 9.8 divided by 2. So that's t. And so all of my every single velocity equation or every single position equation is wrong. No, what do we solve for? Time. Every single time equation has a 2 right there as well. So anywhere where you see 9.8 divided by 2, you know what I mean? And I totally apologize. But from that perspective, you get the velocity. I'm not even saying words right. You get the time where the other y is 0. The y is 0 right there, and then this green path goes up, and then it's y is 0 right there. And you just made an equation for the y direction. You know what I mean? And so this is an equation for the y direction right here, and also divided by 2. And there you go. Then you get the time frames for the And here's t prime, here's t double prime. Where the hell is just t? There it is. So vi sine theta divided by 9.8. Okay, hell yeah. All right, cool. So now, new sheet of paper, we have those time values. This is the time for the green arc. This is the time for the first hop. This is the time for the second hop. And obviously these are wrong. Everywhere where you see a 9.8, divide by 2. And this 2, it was that k, it's the 1/2 velocity. So that's where that comes from. But that is so fascinating how this whole video, you know what I mean? There's probably times where I do it right, but I don't think so. Okay, so now what we need to solve the problem, you need that continuity. You need to say, hey, the time it takes, well, what's this distance d? Like the full distance, that's going to be the time it takes, it goes on the path, times this velocity. You know what I mean? That makes sense to me. Or you just have a position equation. You literally just made a position equation that said, hey, position in the x at any time is equal to v initial cosine of that 45 times t. So this is for the green arc, this is for the first hop, this is for the second hop. This is the position equation, you know what I mean? And then so if you want to evaluate it right here, this point is t prime, and then a separate equation, you know what I mean? This is a separate equation. This is 0, you know what I mean? We're starting at 0 in the x, you know what I mean? So x is 0 for this second equation, and then this is t double prime, you know what I mean? I would think it would be horrendous to actually, you know, I don't know, use this as my datum, you know. No, it wouldn't. It would just be a constant. I could do that, and I should, you know what I mean? If I'm saying, but no. I'm happy to make these two separate equations, and there you go. So now I know that the equation for B is this x double prime. So there you go. There is the equation. And this t double prime is from t is equal to 0 right there to that point. And so when I evaluate, when I throw this into there, hell yeah, this gives me the distance B. Here's the distance A. You know what I mean? To get distance A, I take this and then throw this time at that point in there. Hell yeah. And then same thing here. This distance, I'm just calling this distance T. T is like T final when it gets there. I'm just going to call that T. And so we take that position. The whole thing D is this equation evaluated right there. Okay, and then you do the same thing. Just kind of plug and chug. This thing was like, no duh. Like A is x, this equation x. This is an equation. This is x as a function of t. You know what I mean? And this is what I need to do more. Is just like, because at the end of the videos, I'm like, hell, I want an equation as just a function of time. You know what I mean? Like, I want an equation, I want my angle just as a function of the grass being slow, like the slow downness of the grass, and my initial angle. You know what I mean? So I'm getting better at that. It's like, hey, so this equation literally is a function of theta naught and k. You know what I mean? There you go. And even equations where you're just like, it doesn't look like it's like only a function of time. Well, like even anyway, you know what I mean? Like this position function is also, yeah, so this is straightforward. This position function is also a function of the initial velocity, because you could change that, you know what I mean? So, but just, if you're just saying, hey, this equation is a function of time, everything else is accounted for, then that's the equation. Okay, so, and that's it. And then just plug and chug and then get the answers. Sweet. You know what I mean? And I'm pretty bad at that. Even, like, obviously that glaring error threw me for a huge loop. I apologize. But, you know, even just writing the problem down and then explaining your way through it is just like, no, I can't do that very fast or very effectively. So now we're going to start the actual slog of this whole video. Just if you want to see the whole process. Like, this problem stumped me for a couple days, and I show how do I get out of that slump. And without further ado, hell yeah. Alright, hell yeah. So we have physics and, you know, projectile problem. We got a baseball. Someone's throwing a baseball and they're either going to throw it in a big arc or they're going to throw it and it's going to bounce. And, you know what I mean? Let's say these velocities were the same. You know what I mean? That's the first thing, you know, to make the problem simpler. Well, if this velocity is the same as this velocity, I don't know. Could you tell that this distance is farther than this distance? You know what I mean? And so that's the first thing that we're going to explore. But this is a cool problem because I still don't know how to do it. You know what I mean? And this is where, like, I don't know how to make the magic tricks happen. But we can walk. I'm going to walk you through where I got on this problem, and then we're going to take a detour and throw it in Excel. Because with Excel, I have found a way that, hey, I can just set this up where I do a projectile with some sort of velocity, and then I can have it go up and down, and then I can find this distance. And then I can do the same thing here. Change the angle. It's going to go up and down. The only thing that this problem says is that this is the original velocity divided by 2. Once it bounces, it loses half its velocity. It loses half, and that's in both directions. It's this velocity vector. You know what I mean? Yeah, that makes sense. But anyway, so let's just see how far I got. You know what I mean? So let's start with the green line. We're saying that the baseball player throws at a 45-degree angle, and then so this double bounce is some angle less than that. And you know, even the first graph, like hey, let's say that's the 45. Well, let's say you just throw underneath at a slighter angle, and then you land like right there, and then it starts to bounce again like at that same angle. So they're saying this angle is the same. Well, I mean, even just from that representation, which line is longer? Like, it's totally obvious to me that it's like, oh, hell yeah, the line underneath that curve is shorter. So even right there, that was one example of like, hey, is this blue line, you know, for sure going to be shorter than the other line? And I guess I want to do one more thing, because I want to say, hey, I'm just going to get, like, that's the other thing, is like the way it's drawn, just guess, you know what I mean? Say that looks like this is going to be like 1/3 d, and then over here it's 2/3 the total distance. You know what I mean? And it might look like this is just a little bit bigger, and so you could guess that actual number. But from that representation, I'm going to actually just make this path a straight line and a straight line, and then I'm going to go to 1/3, 2/3. You know what I mean? And then I'm going to well, I mean, obviously I can't have it at a 45, so we're just going to pick. I don't know. Maybe just a 30-degree angle. You know what I mean? So if we chose a 30-degree angle, sure. I mean, we got to choose something. So if we chose a 30, so this, and we're going to say, hey, this is, I'm just going to call it L. I don't like that D. So we're going to say, hey, this is the full length. So if we do this for this triangle only, we want to know that distance. Well, this is L divided by 2. This is L divided by 2. We can use Pythagorean's theorem that says a squared plus b squared is equal to c squared, which is that. And c is the square root of a squared plus b squared. A squared and b squared are the same, so we could be 2a squared square root of that is c. So now we can say a is L divided by 2. We're going to square that. That's L squared divided by 4, or just L. This becomes L squared divided by 2 squared. That's a very useful representation because it helps you get to here a little bit easier. And then multiply by 2, so we would have L squared divided by 2, and then the square root of that. Same thing. You take the square root of L divided by the square root of 2. You take the square root of L squared. You know what I mean? So visual representation of why that goes to L, this goes to square root of 2. And then, you know what I mean? We have 1. We have this distance as 1 divided by the square root of 2, L. And now let's see if that makes sense. Because the other way to do a check on reality is 1 over the square root of L, and then we could say cosine 45. Well, that has to be L divided by 2. So cosine 45, and just by definition, cosine 45 is 1 divided by the square root of 2. 1 divided by the square root of 2. Square root of 2 is 1.14, and 1.14 divided by 2. No, I'm sorry. 1.4142. That's square root of 2. But anyway, so these would multiply, and you would get 1/2 L. So yeah, that distance is 1/2 L, and we got to check on reality. Okay, so this distance has 2 of those, so this full distance for the green line, we're going to say the travel path. Travel path is going to be, well, 2 square roots of 2. Okay, so now let's do, if we did 30 degrees, you know what I mean, what would be, so this is 2/3 L to there. So that means that this is just 1/3. So let's do that 30-degree angle. We have 1/3 L, a 30-degree angle. And now what the hell is this? Well, we can just do straight up sines and cosines. We can say, hey, if this is the angle 30, the sun is shining on this one. This is your sine component. Sun is shining on the sine, and this is your cosine component. So let's just do the 1/3 L. And now what do we do? And so if we take cosine 30, you know what I mean? So we have these two values. We have cosine 30 and then this length. And this length is smaller, and we want the bigger length. So do we multiply these together? Because if what the hell is cosine 30? Well, it's a fraction of a whole between 0 and 1. You know what I mean? It's somewhere in between there. It could be 0.9, it could be 0.1, you know, it could be anything, but it's a number less than 1. So if we multiply a number less than 1 to this would go down. So is that what we do to get the bigger number? You know what I mean? We know this one, and then we know we can take some sort of representation of cosine 30, but we do want the bigger number, the hypotenuse. So hell no. We take this number and then divide by cosine 30. Dividing by a 0.1, dividing by a 0.9 always gets you that bigger number. Cool. So we have 1/3 L divided by cosine 30. Cosine 30 is just 1/2. Okay. So now we have 1/3 divided by 1/2. And then so dividing by 1/2 is the same thing as multiplying by 2/1. You know what I mean? So, and you could say this, the 1 stays downstairs, but the 2, hell no, goes to the top. So now we got 2/3 L. So 2/3 L, and I feel like we messed something up. Maybe not though. So if it feels like we did. Oh, no. Yeah, exactly. Cosine 30 is 0.866. You know what I mean? This is 0.5. I was just saying there's no way that with a cosine 30, I know that this is 0.5. Sure, whatever this hypotenuse is, this is half. But this is an 86.6% of the hypotenuse. So no, cosine 30 is 0.886. So we divide by 0.8 or 866, and we'll do that. So we'll go 1/3 divided by cosine 30, and yeah. So instead of 1/3 L, we get 0.385 L. Okay, so now we have a check on reality, because if this is 0.33 L for this distance, yeah, this distance has to be a little bit bigger, and there it is. We're going to multiply by 2 times 2. I'm going to store that as alpha A. So now we at least know this path length is 0.770 L, and this is L. Okay, so now we want to know this one. So this one is going to be 1/6 L. So we're going to do the same thing. 1/6 L. Now we're on a roll. Cosine 30. So 1 divided by 6. Well, yeah, 1/6 divided by cosine 30. And heck yeah, we get 0.1925 L. Alright, sweet. And I don't know, you know what I mean? If you want me to write bigger, but I just want to stay on one page, just talking through it is what we're getting at. Okay, so now we know that that this, did we multiply by 2? No, we just got one of them. And is that going to make sense? 1 divided by 6 is 0.166, so this hypotenuse is 0.1925. So there's a check on reality, you know what I mean? Anytime you're doing this, you're just like, well, this should be about the same, it's just a little bit bigger. And it is. And we're going to multiply this number times 2, store it as alpha B. So now we have the path length of this. This is 0.38 L. So 2 divided by the square root of 2. This is going to be 1.4142 L. So let's add these up. Alpha A plus alpha B. So this blue path length is 1.154 L. And we're just doing an estimate. So obviously this path length is farther. It's going to take longer time to get there. The whole idea of this baseball problem is you want to get the person out after you threw you want to get that baseball there as fast as possible. You know what I mean? Lowest amount of time. And so taking the farthest route, you know, that ain't no good. You can take a shorter route. But once it bounces once, you lose your velocity. Obviously, if the velocity didn't change, hell yeah, you would just roll it across the ground. If the ground wasn't producing any and that's a good, you know what I mean? I was struggling how to make this problem, like, even chop it up into simpler things that just made sense. Not that they're going to help you get to the answer any faster. But yeah, if we don't have friction with the ground, you would just throw, you know, totally perpendicular, kind of rolling the ball at whatever your initial velocity is, and it would get there the fastest. That would be the fastest. But this problem is cool because the second that ball hits the ground, hell yeah, friction. And you just lost. And in this problem, they're going to say you lost half your velocity. And usually these problems are pretty darn good, where that could be a good representation of what happens in a MLB game. All right, so now, even from that representation, you know, so I'm going to take a step back because I haven't solved this, but even that's the place that I wanted to go. You know what I mean? Ultimately, the other place that we're going to go is to Excel. I can say that F equals ma, and then we can say that acceleration due to gravity is 9.8. Then I can know the velocity, you know, initial, and I can get an equation for velocity. You know, based on integration. I can integrate the acceleration. We're going to do acceleration is dv dt. So all that cool stuff, and we can get an equation. We can get an equation for velocity and position of the green path and velocity and position of the blue path. And then in Excel, we can just kind of manipulate, because it says what angle. Well, we can make an Excel sheet where we can just change this angle until we actually get everything to line up. So that's basically what I wanted to do with this video, but sometimes I have to, you know, we're learning how to learn, and so I'm going to stick with this, you know what I mean? I think I can get a little bit. What I want to see is, like, well, is this faster? One, we know that this distance is shorter, but this velocity is half. So now we need to see. So, like, what representation could I do? Like, I'm just gonna say, I'm going. Let's say this is. Oh man, what's the way to do this? This is distance. Yeah, let's say this is 141 miles. Okay, and this is going to be alpha A is 77 miles, and this is going to be 38.5 miles. Okay, hell yeah. So there we go. And now we're going to say we're just going to travel with initial velocity of 60 miles per hour. That's usually pretty good. So how long is it going to take to go 141? See how just making the problem like that, you're like, oh, hell yeah. And that's the deal, you know what I mean? Especially when you're doing like problems in meters per second, you have no idea what a meter, you have no idea what like 100 meters per second is. You know, is that terminal velocity? Sure, 120, like 100 meters per second times 2.25. Yeah, you're going 225 miles an hour, you know what I mean? And actually, I don't even know. I think terminal velocity is 120, so divided by 2.25. See, I have no idea even what terminal velocity is in meters per second. You know what I mean? So there you go. It could be, I think you're only going 120 miles an hour, you know, at terminal velocity, but 53 meters per second. See, so you just don't have any good representation. But the second you're saying, hey, we've all been driving 60 miles per hour, unless, unless you're, I mean, the speed limits now are 80, but you know, there's plenty of roads that are 60, and you're just like, hell yeah, for every hour I get to go about 60 miles. Okay, so right here, just really simple, 141 divided by 60, it's going to take you, this green path, 2.35 hours to drive that path. So now, this problem says, hey, you're going to go 60 miles per hour on this path, but once you get to this distance, you know what I mean, now we're just going to finish the trip going 30 miles per hour. Maybe indicative of like driving a pavement and then you hit dirt road and you're like, damn it, it takes a long time on dirt roads. They're kind of miserable to drive on. Okay, so we have that, and this is going to start as alpha A, and this is alpha B. Obviously, it's times 100. So alpha A times 100, and or I'll just use these values. So we got 77 miles divided by 60. You know what I mean? So, oh, and let me store these. So 141 divided by 60, that's 2.35. That just came right out. 77 divided by 60, I'm going to store that as alpha D. And so we have a time of 1.28 hours. Okay, hell yeah. So even just right here, I can do some simple math in my head. 2.35 minus 1.28 hours. Well, I got another hour to go that distance. You know what I mean? And we're past the halfway mark. You know, so I mean, it just looks like this is going to be faster. And now we can run the calculation and say we have 38.5 divided by 60. It's going to take 0.641 hours. And we're going to store that as alpha E. So now for this blue path, we have alpha D plus alpha E. This 1.8 hours plus 0.64 hours, alpha D plus alpha E. And so this trip, the blue trip, is going to take 1.925 hours. And for sure, so that's way cool. So now the problem in the book says determine the ratio of the times for the one bounce and no bounce throws. And you know, alright, hell yeah. I'm so glad I watched my video because we do have an error. This was so dumb, you know what I mean? We had such a good learning opportunity to see that this blue path would have been longer, because now what they're getting, obviously, because I made a mistake. We're going 30 miles per hour. So this distance, and what did we say? I have to actually go back and see what this was. But yeah, this was 0.385, so 38.5 miles. And so we'd go 38.5 divided by 6. See, I'm doing the same thing. It's 38.5 divided by 30. Whoops. 38.5 divided by 30. So this path would have taken 1.28 hours. And I said, hey, what's the distance? 2.3 after I did that small calculation, 1.28. Yeah, we only have 1.07. We only have just over an hour to do this. But you can totally see that this is, I can only go 30 miles an hour, and this is 38.5. So obviously this blue path would be slower if I hit right there and then start down a dirt road of 30 miles per hour. We'll have to reduce my speed by half. So how does this problem work out? Well, it says, hey, let's take a shallower angle, because now I'm just going to go here. This is also a bummer, because it's going to work with the parabolic shape, because if I do a shallower angle, I'll actually... well, I guess that there is no rhyme and reason to this D, because and I'll just give you the heads up. The D in the book is 1/5 over here, and then the D right here is 4/5. You know what I mean? And so from that perspective, you're almost already there, and then you have, like, because you reduced it by half, this second parabola is just real tiny. I mean, this one's nice and big with that speed, but the second your speed goes to half, it is just a very small bounce before it hits the earth again. And so, but with that, this triangle gets more long, and then, but you will get where this blue line is less time. But yeah, I just wanted to make that error. It wasn't 1.9 hours compared to 2.3. In this scenario, this blue path would have been slower. We should have gone the green path and had our ball not lose half its velocity. And then in this, but we're just doing like a very rough idea of what's going on. So anyway, so that's that. Let's get back to the video. All right, sorry about that. And I didn't understand that problem, you know what I mean? And so I have such a better representation doing these little triangles. That was groundbreaking. Today I was like, yeah, I could probably do triangles and then get a sense of what the hell's going on. And even from that, I can now move from that point being like, there's something about being a student where you're just like, we are just like way too skeptical, or we just know that if we multiply the wrong things together, we're just going to get the absolute wrong answer, or just lose all sense of understanding of the problem. So there's a huge element of just like, I will believe it until I see it. And sometimes getting the right answer to the specific problem is when you do believe that's what happens. But that's still very magic trickery. You know what I mean? It's still like, hey, massaging the equations, getting, continuity, and making everything perfect. If that helps you with your understanding, it all does. You get the endorphin rush of actually getting the right answer. But like even just like right here, having this fundamental understanding, it's allowing me to go to the next step. And be like, oh, so I can actually answer this one. And we already answered this. Like if you just throw like 41 degrees and you're just underside that arc, I'm just going to say, hell yeah, you are faster. And that's all they want. So it's like determine the ratio from when you shouldn't do a bounce and then when you should just do a bounce all the time. And so now, crap's not going to happen right here. It's going to be always, even if you bounce within the last inch, you should bounce because it took a shorter path. But now, so now what I'm seeing is like, well, what if I threw at just a horribly 1 degree angle where, it hit like right here, And even you could do a shallow angle, visibly like right here. So let's say that was the angle, and then it's just half the velocity. Even though it'll probably bounce again, But we're not really worried about in this scenario. We're just what we're gonna say is like, hey, what's the angle where if it does bounce once, because that was where this problem kind of messed me up. Is like, well, it seems like you only have one angle. There's actually only one angle where if you do bounce it, it's going to go back up into the air and then land before it hits again. So that's yeah. So that's what would happen there. So I still don't understand this determine the ratio of one bounce. Because obviously, if you had anything shorter than this, then you would probably bounce like twice. Oh, is that what it's, Let's say, so let's read the problem. Because if it's actually saying every time it bounces, it'll lose half its velocity. It'll go from v divided by 2 divided by v divided by 4. Like, I'd be interested in that problem. I just, for the life of me, do not understand what they're asking. And that's just the nature of problems. But we can read it. So, ball leaves the ground, same angle, both scenarios. What's the ball's speed after it bounces? But the ball's speed after it bounces once is half of what it was before the bounce. Assuming the ball is always thrown with the initial speed, always thrown initial speed in both scenarios. What angle should the fielder throw the ball to make it go the same distance with one bounce in the blue path as shown from the upward throw at 45 degrees? With no bounce, and determine the ratio of times for the one bounce and no bounce throw. And I just had to look in the back of the book. It was 0.994. It was 99.4%, of the time that you would do one bounce, and then a very 0.6% of the time ratio you would do a no bounce. But maybe it is over here. You know what I mean? Because if I'm reading the problem right. No. Well, obviously, obviously there's only one place where this ball can bounce and then actually reach this. And we just did a scenario where we were like way under the time limit. You know what I mean? It took 1.925 hours and 2.35. So there is a scenario where, like, hell yeah, I could bounce 3 times. But I just, for the life of me, I don't think that's what the problem is asking. I think it wants to know, and maybe there is something. Maybe I'm miscalculating this, where if you had like these going at basically a 44 and a 45 degree angle, and that's what I could run in Excel just to see what the hell they're talking about. So if we do run that angle, and then it did get here faster, but just barely, but now it has to bounce and then lose half its velocity, you know what I mean? Maybe, and obviously it's going to be like at the, it's not going to be on the ground, but still this might not get there faster. I mean, visibly, there might be something funny there where, yeah, it does slow by half, and these two paths were about the same, but the fact that it slowed to half for this last little bit, maybe that is what caused the scenario. But this problem could be way more complex, where you could do 3 bounces. And I think even in Excel, I could set up an equation that says, hey, every time it bounces or crosses this axis, because in Excel I'm going to do this. I'm going to run an equation that maybe kind of goes like this, but it's just going to be, instead of doing this, it's going to be an absolute value. And I guess every time it hits this this origin, I mean, I can just manually, I don't know, it'd be sweet if I got an equation where, yeah, the velocity reduces by half, because now, yeah, you could take another bounce. If you have all that time to get there, you could do this, and then this, and then this would be v divided by 4. So full velocity, half, and then a quarter velocity, and to get there. Okay, so I actually probably am going to pause, because I would like to finish, with a very robust understanding of what this distance is going to be. Because even when I solved it, this distance, the continuity of this distance, like, it gets to be like, well, okay, I have 4 equations and 4 unknowns. You know what I mean? 4 equations and actually 5 unknowns, and then I have to set a continuity that the time it takes for this path to get to here, I think, what the hell is the continuity? I mean, we're gonna have velocity in the x direction due to this green graph, and then the time frame it takes to actually, yeah. Anyway, I don't even want to do that. So here we go. We're gonna go straight to Excel, and this is how I would set up this problem. So a little preamble, but the equations that we're going to use is acceleration, is a derivative. So this is really cool. We get to use the fact that, hey, we do have a derivative, and we use it from the basis that the definition of acceleration is change in velocity divided by change in time. Even just spelling out the words and then going for, change in v and change in t. And then finally doing a dv dt. Kind of means the same, it just means it's kind of a smaller change in time. Well, that's exactly what we're going to do in Excel. The first column in Excel is time, and we're going to go like 0 seconds. Then we're going to go 0.1 second. And we could even reduce this. We could go we could go 0.01. We could go 0.001, and then just, make the Excel sheet just a little bit farther. Okay, hell yeah. So the other equation that we're going to use is velocity is change in position, like change in x, change in time. Now the only other thing for this problem is we definitely need to know we have 2 different directions. We have the x direction and the y direction, so we kind of have two different things to find. So velocity is also change in the y, change in time. And so what we would call this would be velocity x, and this would be velocity y. And then same thing here. We would have acceleration x is velocity x, acceleration x, and then so hell yeah. So now we could do acceleration y is dvy dt. You know what I mean? So we got the basis understanding, and now we know that we have two different components for velocities and positions. So now with this, we'll ditch the subscripts for now. Oh, no, we just kind of defined it. But just in general, velocity is change. Alright, holy Toledo. So I lost 10 minutes of footage, and I'm going back and editing this. So what we're doing is we're setting things up in Excel. Why we do it is because we have this equation F equals ma. And if we know something about the change in velocity, you know what I mean, then we can, and this is change in velocity, change in time. So what we do in Excel is we start at 0 time, and then for our equation, well, we are going to have some sort of initial velocity. So velocity x, velocity y. And then we're going to have a change in time. You know what I mean? And that's the definition of acceleration. You know, it's going to be a change in velocity and change in time if we have acceleration. And so what we did is we did a free body diagram. We still have a baseball. You can still do a free body diagram. You can chop this. Oh, let's get some more light. Alright, so you can chop this out of outer space, and I do. So my method of doing free body diagrams is chop the object you want, and then pretend it's like in deep space, away from every stars, no gravitation, and then, so that's what we do. That's the mass that we chop out. The F equals ma part. The A part says, hey, can we visually see motion, you know, of any sort? And in this case, we do. We have some sort of velocity. So cool. And it's going in this direction, let's say. But if we're in deep space, it's just going to go that direction forever. That's kind of Newton's laws. And so, but if that's not what we visualize, so even over here, what do we see? We see a baseball go up and then down. You know what I mean? We see a baseball go over. That might be harder to see, but we definitely see it go up, and then, whoa, it came back down. So we know, at least in one direction, it's going to have a change in velocity. Cool. And then and then that brings up the whole idea of projectile problems, is you kind of have two different directions. The first thing I do on the free body diagram then is to, so this side is like, well, if we do see something, you know what I mean, why do we see it, and are there forces? So if this isn't 0, if it's not just a bridge at rest, you know, acceleration is 0, or just a constant velocity, you know what I mean, even if it is 0 and a constant velocity, we still have to go over here to identify if there's any forces. And you know what I mean, obviously there's an earth underneath this baseball, so for sure there's going to be a force on it downward, you know what I mean. And so because of that force, you know what I mean, that's going to be the force of gravity, which is g m mass of the baseball, mass of the earth raised to the earth squared. And so so that's that. And at the end of the day, if you plug that in, you know, you plug this force, you know what I mean, this is the force out of the book of what we observe in the universe. You plug it in that side, so then you get g m1 me divided by radius of the earth squared is equal to m1 again over there. So the mass of the baseball cancels, and now we have an equation for acceleration. Basically it says, and then g me divided by radius of the earth squared is just 9.8. So it's just a longer way to get that if you do have a mass like a baseball, you have a weight on it of mg down. And that weight is a force. You have identified a force in this direction, and therefore F equals ma. If you identify a force, that force acts on a mass, and you must have acceleration. You know what I mean? So yeah, hell yeah. And cool. And in this case, if you did it this way, force is mg, well, this is the book force over here, so you would have mg is equal to ma, you know what I mean? So that's how you would do it. The forces go on this side, and then it's just equal to ma. You know what I mean? Straight up ma. And this can, and in the y direction, hell yeah, masses cancel, but your acceleration of that baseball is g. Now if you did it the other way, in the x direction, well, is there an earth over there? Is there an earth over here? No. That's the most interesting thing, and I think that's the take-home point, where you can take a free body diagram, take this thing into deep space, and have it go, have a velocity in this direction. It's going to keep going in that direction. Well, cool. Bring it back to Earth and have the velocity go in that direction. Guess what? Same thing. You have an Earth underneath you, but this thing will not slow down. And I think that's fascinating, because the only thing that's going to have it slow down is the fact that it's just going to run into the Earth and stop. Now, this is neglecting air resistance, but you could set up a scenario where you're just in a huge vacuum chamber and throwing balls, you know, with robots through the vacuum chamber, and you would still totally see constant velocity. There is no forces. There is no mass sideways. Maybe, and I did say, well, maybe you have the, you know, the moon over here and the sun over there. Sure. Then you've identified a force. It's a distance away. That's a mass. This is a mass, and you use Kepler's equation. But that's going to be negligible for this problem. Okay, so that's what we get. We get the acceleration in the x is 0. And so so this next, these were the two columns that we set up. We set up time, and then the column of, hey, in the acceleration in the x is just going to be 0 all the way down. Acceleration in the y is constant. It's going to be negative 9.8 all the way down. And so we start at x is equal to 0. We do know that we have initial velocity sideways and up. And then and so how do we use this acceleration? Well, we go back to the equation and say, like, the equation of acceleration says acceleration is dv dt. And in this case, this is an equation. You have 3 different things here that you can solve for whatever one you want. And we want to solve for the change in velocity. That's kind of every time interval, we want to know the change in velocity. So the change in velocity is the acceleration times that time interval. Now we're going to use a time interval of 0.1. So this is going to be acceleration, you know, so it's going to be like 9.8 times 0.1. So we're going to have a change in velocity of 0.98. Basically 1 meter per second every tenth of a second. Tenth of a second. And so that's going to be that column. Once we know the change in velocity, well, at the next time column, we're going to have once we know where the hell's change in velocity. But anyway, that kind of gets you there. And then you do the same thing for position. You say velocity is equal to change in position, change in time. Now this is the equation. You got 3 things. The only thing about this, though, is this part has to be an average velocity. So if I have a velocity at time 0 of this, and then a velocity at time 0.1, I have to add these and divide by 2 to get the average in between them. That's the only thing that you have to focus on. So we do that in Excel. So once we do get the next change in velocity, we can average them, and we're going to use that value for this, and we're going to rearrange this equation because we want change in position. Change in position is velocity average times change in time, and this is going to be that 0.1 minus 0. So we take those, and we do this in Excel. So now we find change in position. So now x is the initial position plus that change in position. Okay, so that kind of sets you up, and now we can move on with the video. We explain more about this, but then we take it to Excel. Alright, hell yeah, so back at it. And, you know what I mean? I like how I'm writing small, and I like how I'm talking fast, you know what I mean? I think this is good, because else if I talk slow, it's just going to be twice as long, and I think as long as my brain keeps on moving, I think it's a good strategy. So we were saying the baseball is going to be thrown at 35 meters per second, that's 80 miles per hour, that's pretty sweet. And so what's the initial velocity in the x? Well, that's going to be v cosine 45. So I'm going to say this is v, so we're going to go v cosine, the theta, and 45. This one is going to be v sine, the theta. Cool, so we have those. You know what I mean? I think in Excel what I will do is time, x, y, v, vx, vy, and then ax, ay, and then have all the other changes, you know, on that side. Because then when I go to graph these, I can just, or I just even visually look at it, I can see my velocities and I can see those. So now, but now we, so we have that initial. We just found the change in velocity in the x is always going to be 0. So how do we account for that? We're going to take, hey, this, so we're going to do this plus, you know what I mean, let's say that. So there you go. And that's going to be our new velocity, you know what I mean. Velocity in the y, we are going to have a change in velocity. We have a positive, you know, y velocity, so we're going to take that, and then we're going to add it to that, you know what I mean. And so when we do that in Excel, now we'll have our new velocity. Okay, so now we kind of will do, and this is the velocity at time 0.1. So now the next thing that we need to do is find dx, change in x, and then we need to find dy. So we say that velocity in the x is dx dt, and then we solve for dx. So dx is velocity in the x dt, but this is the only one where it's just like, well, alarm bells have to go off. This is Vx average, you know what I mean? So we have to figure out what Vx average is. And so, and even in Excel, I could do V, you know, the next thing over, I would just do Vx average and then Vy average. And then these terms are just going to be, well, the initial plus, I'm sorry, it's over here. It's going to be the initial plus this divided by 2. So in this case, Vx is always the same, so Vx average is just Vx all the way down. But the Vy, we're going to have an initial velocity up, and then this next term is just going to be up, but it's just going to be a little bit smaller. You know what I mean? So just a little bit smaller. And then so our velocity will be, our velocity average will be that term plus this term, and then divided by 2. So now we have our velocity average. And it's these that we can throw into this equation. Cool. So now we can find dx dt is going to be that multiplied by that 0.1 minus 0. Cool. And this is where the time frame comes in again. You know what I mean? We're taking something, multiplying it by the change in time. And we did so over here. We took something, the acceleration, and then multiplied by the change in time. That's why position is a second order, or you know what I mean. Like downstairs, if you did acceleration, d2 dt squared, you know what I mean. This term would be squared downstairs. The second derivative of acceleration is position. All right. So hell yeah. Now, and I guess we're gonna, you know, might as well make long videos and then go through this again in Excel just so we get it right. But now we have what the hell did we even find? We found dx and dy. You know what I mean? So now we found those. So now our new x is going to be, hey, this original x plus our dx. There you go. And this is going to be our original y plus dy. And now the whole process can start over again. At that new time frame, we have an acceleration that's going to cause those changes in velocity. So our new velocity at the next point will be the last point, you know, plus these changes. That is going to be important because now we're going to take the velocity averages between the last point and this next point, and then we're going to throw it into the equation for change in position. That's going to be the velocity average times the change in time. And then from those change in positions, we're going to get our next change in position. Cool. Now the only thing that's going to happen is that this one is going to hit this x-axis and then just keep going like this. You know what I mean? Because we're saying we do have a change in velocity. It's going to, let's say we have a velocity or just whatever, and it's upward. Well, it's going to, every second, is going to go down 9.8, 9.8, 9.8. So if it does do that, the velocity is going to keep going negative. And so what we want to do is in Excel figure out a way and I guess I'll just get to it, to when this does hit 0, or our position, like our y position is a negative number down here, that it registers as a positive number, but if it's so this is where we'll have to do this, because let me see if I can actually just explain this. So we'll have at some point our position our position in the will be negative, something. Our y position will be negative, and then what we want to do in Excel is just say, hey, let's pretend it's positive. And if we pretend that it's this is what we want our graph to look like. This, yeah, sure, past this, but we don't want that negative acceleration to be. We want that acceleration to actually switch. We want that acceleration to be positive 9.8. So then our graph will look like that. So this is what we can do in Excel. Get a graph that looks like this, and then have that acceleration change to bring those negative y's back the other direction. And we can do it in a simple way, kind of a classy way, where it goes to this point and then it just hops. So the way that we need to do that is, because the second it hits, it's going to have some sort of velocity that's in this negative direction. And I guess I haven't thought this one 100% through, but let me talk it out. Yeah, the velocity will be negative, and then so from here the change. So I want to always register the absolute value of y. So y is always going to be the absolute value, but the velocity is still a negative component, and I think that'll make sense, even though. Well, let me just get to what I was thinking. If we're saying where the absolute value is up here, if we do the absolute value of y, we're going to have a little bit of a y, and we're going to have a negative. Oh shoot! I haven't thought this all the way through. So let me just do it in Excel and see if I can explain it after the fact. All right, hell yeah! So we're in Excel and we can just start going for it. Here's our time, and we have seconds, and we're gonna go 0 to 0.1. Do a reasonable time interval right off the bat, because then we can increase it for our next go around. Okay, so I'm just going to look at my chart. So now we're going to have position X. This is going to be in meters, and this is going to start initially 0. So now we have Y in meters, and then this is going to be 0. Now, and then we'll do the manipulations with the absolute value. But it's just nice to do something and then make a chart and see if we're actually doing what we want it to do. So now this next one's going to be velocity X. This is in meters per second. I'm just going to copy that, and then we're going to go velocity Y. Alright, in meters per second. Now I'm going to go acceleration. Yeah, might as well do it this way. So now we have acceleration X in meters per second. I'm going to write it like this. It's meters per second and then divided by second. You know what I mean? So then it's just obvious that it is the change in velocity divided by change in time. Cool. Whoa. Alright, so just write change acceleration in the y. So now we have acceleration in the x, acceleration in the y. Okay, so now the next thing will be those d's. So the first equation is acceleration is equal to dv divided by dt. So this will yield dv is equal to a times dt. Hell yeah. And so let's do that one. So now we have dvx, and that's going to be, well, we can do, acceleration in the x is 0, and then this one's just going to be a constant, negative 9.8, and then a couple stars on here. Just, I'm trying to get better at, like, hey, you know, if I did make a mistake, well, obviously when we drag all this crap down, this one's just going to be 9.8, you know what I mean? So I could just do that, but I did the stars because I don't want to get it too busy right now. Okay, so hell yeah. So now this dv, the equation says dv dt. So no, I'm sorry, dv is the acceleration times dt. So this equation, go to my acceleration, and then times, and you know, this minus this. And you can see, I don't even know why the hell I'm doing this, because it's just going to be 0 always. So now we're going to go dvy. Now this one will generate a change in velocity, because the equation is acceleration, negative 9.8, times this, the difference in time. There you go. So every 0.1 second we'll have 0.98. If we had a full second, we would change the velocity by 9.8 meters per second. But you know what I mean? If we're only having 35, so you know, going back to check on reality, if we have 35 meters per second going this way, we might only have like, let's say we have 25 meters per second going up. Well, that's significant. So yeah, this thing's going to be in the air. So just even right there, there's a check on reality that initially in 1 second it's going to go from 25 to you know, 15. Well, let's just say it's 20 meters per second straight up. In 1 second, it's going to only be 10 meters per second squared straight up. In the second it's going to reach, you know, it's going to have velocity of 0, up or down, and then yeah. So that's kind of interesting. I wonder actually how long this thing is going to be airborne. I thought some of these projectile problems could only be like, you know, like 3 seconds. Like 5 seconds would be huge, but maybe 3 to 4 on this one. Okay, cool. So that'll be a check on reality. Make sure we do things right. Okay, so we have that change in velocity. We even just right now we can just go for it. Oh no, we got to do this velocity initial. So this is what we're gonna do. We're gonna do velocity initial is 35. Cool, and this is gonna be in meters per second. Now the other thing that we want is the angle. So we have theta, and degrees. That might just be obvious, but we'll have 45 degrees. Cool. So now we know this velocity in the x. That's going to be our input velocity times, and then here, anytime that you're not going to drag down a value, you got to go function F4, $ on both. Okay, cool. Now we have in the x, it's the cosine component of 45. All right, booyah. So we have that, and then the y component, it should be the same. It's just going to be a sine component. So we have the velocity, and $, function F4, and then we're going to go times the sine component of the angle, 45. Oh, and this is going to be $. And I probably made an error, you know what I mean? Because right here, what the hell did I just do? Did I just do it twice? No, I did it, but we need $signs on this. Because if we do $signs on it, now we can pull this down, and those values, those two values in that equation will stay put, you know what I mean? And we don't even bring those down. So, you know, for that reason, there was no reason to do $signs, but okay. Because now we found our change in velocity. So at this next time frame, we're going to have, this is the equation. It's going to be the original velocity plus just our change in velocity. Straight up easy. This one's going to be velocity in the y plus the change in velocity. And I do plus because, look, change in velocity is negative. So there you go. It went down a little bit. Okay, heck yeah. So from this, we have dvx. We have the change in velocity. And now we have the new velocities. But for the next equation, we need to go velocity is equal to dx dt. It's change in position, change in time. Therefore, we want to know dx is equal to, well, it's that velocity times dt. But this is going to be, you know, 3 stars. Velocity v is equal to v average. You know what I mean? So so now we will write. And I could have just wrote V average. You know, we might as well. So we're going to go V average. Cool. Hell yeah. And so now we can say Vx average, and then we can go Vy average. So this V average is the initial x. I'll do parentheses because I'm initial x plus the next velocity divided by 2. So now that's going to be the average velocity. But the cool thing about doing this in Excel is everything is just adding and subtracting. It's very basic, and then kind of multiplying by the change in time. But that's what I'm getting at. It spells it out for you. You know what I mean? It's just like I believe this is what's happening because I did the F equals ma. You know, I've identified a force, and on a mass, force of gravity on a mass that's going to cause a change in velocity. That is this value. And now I can run a change in time because I know acceleration is a change in velocity times change in time. Make this small. Well, yeah, my change in velocity is small, but it's accurate. And then we can just play this whole thing out. Okay, so velocity average in the y is is equal to parentheses initial plus the next one divided by 2. And I'm just going to check my equations. Perfect. Okay, so now we have that velocity average. Now we do want to know dx and we do want to know dy. You know what I mean? Because same thing. This velocity in the y is equal to dy dt. And if I throw more variables, I do less variables just because they get so confusing. Too many letters, you know what I mean? So now you have what the hell did I even do? This was velocity in the x. This is the average velocity. So velocity in the x average is equal to dx dt. There you go. So now we're going to say this. Velocity in the y average dy dt. And then rearrange dy is equal to velocity in the y average times that dt, change in time. Okay, now we're just money. Now we can do this. What the hell is the equation? Velocity average times change in d. Velocity average times the change in time. Okay, booyah. And then we can go dy is velocity in the y average times change in time. I mean, it is tedious, and you might make errors your first time, but you know what I mean. At least you have this one. You know what I mean. At least you have a video where you could set it up, and then because that's the thing. The human brain will just cause errors where it wants to or something, and you just won't realize why you're causing errors. Even I'll watch my videos, and for the life of me, I can't say volume. You know what I mean. I made an integration, and I would just kept saying area. You know what I mean. Hey, look at the area of that sphere. You know what I mean. It's like, no, the volume of that sphere. You know what I mean. So even just little hiccups in the brain just doesn't process things 100%. Okay, so now we have this change in x, change in y. Well, guess what? This is just going to be, our next x value is going to be the x original plus the change in x. And then we have y is equal to the original plus the change in y. And, you know what I mean? We don't have any change in velocity in the x, but we do have a constant change in position. So see how that integration kind of works? You know what I mean? So right here, my next velocity in the x is the absolute same. You know what I mean? It's the same number, just like acceleration is the same number. But here, my position in the x does increase. It just increases linearly. Where position in the y, no, it goes up and down with a with an x squared negative x squared equation. Okay. So now we're just good to go. Let's fully drag this down. But yeah, no, I want to do that later, just because it's kind of fun. We'll drag it down once, and drag this one down once. Whoa. And then we can see this is an equation, so we can drag all these equations down. So heck yeah. So now I can just do this. Drag this whole thing down, but 3 stars on this because this number will mess up. So drag it all down at once. Oh, it didn't mess up, so that's good. All right, so now we're just good to go. And so what does this say? It says, oh, holy hell, this isn't good. No. We just need to run the time frame just so much longer. You know what I mean? So yeah, we just do need to get to. So I'm just going to be very cautious, and so it doesn't mess up. We're going to go 0 to 1, and then we're going to run this to 5 seconds. There can't be any projectile problems that are above 5 seconds. You know what I mean? That's kind of my rule of thumb. It would have to be, you know what I mean? Even a baseball off a bat ain't going to take 5 seconds. But it might prove me wrong, but it didn't. Because now we go, no, does it? Damn. Oh, is this proving me wrong? Or am I just, you know, I feel like that was an axiom that I've always used. That like, hey, if any projectile problem up or down, like dropping stuff. But I guess if you're throwing it up and then having it come down, it could be 3 seconds up, 3 seconds down. Never thought of that. So let's get this all the way at 8 seconds and then prove me wrong. You know what I mean? That's the crazy thing about having preconceptions with equations, is you're just like, no, you want to make it work. And then you, like, I did the 3-point basketball problem, and I was, you know, it's just like the second a number gets wrong, you're like, I wasn't wrong. It's the problem's wrong. You know what I mean? And then you're just trying to make everything work. But you know, we'll have to keep an eye on this. There might be an error. But hell yeah. So now here's our position in the Y. Baseball goes up, and I guess it goes up hella. I feel like it's not that. If it's not possible. No, I mean my change in time is 0.1. So like like my velocity every 0.1 seconds goes down 1 meter per second. You know what I mean? Because this is in meters per second. And there you go. Okay, so oh, I hate when it does stuff like that. There we go. Okay, and let's follow the Y. So the baseball goes up. And then at some point it comes down, and then at some point it crosses the ground. You know what I mean? And so it takes 6 seconds. That blows my mind. But I guess 3 seconds up, 3 seconds down, so it still makes sense. You know what I mean? Yeah, that's pretty wild. But maybe my speed of 30 miles per hour at a 45-degree angle at 80 miles per hour, but a pitcher can throw, 100. So can't an outfielder throw at least 80? So hopefully I'm pretty good on that. Okay, so now we have that equation. But what I want to do, and this is where I'm going to pause the video, because I have to come up with this one myself. There's no way I can just, you know what I mean? It might even take me half hour. So all right, catch on the flip side. All right, hell yeah. So we're back, and you know what I mean? Well, what we did, the first thing I did is I just made this column an absolute value of y, because y does go negative. But what we're going to see is once y goes negative, check out y. You know, this column, it just keeps going negative. You know what I mean? So that's the bummer. So if we actually just plotted y, and we're going to go to, this many seconds, and we're going to go insert scatter plot. So there you go. So y, instead of bouncing, you know what I mean, it just goes this way and then just keeps going, because the velocity, and let's look at this from the parameters of what's happening. So at this point, or what do we have? We'll just go back to here, is the acceleration is always in the negative y direction. So we do have some positive y the change in velocity. So this is positive y velocity, but the acceleration due to gravity always makes that downward. But we want to model it where it looks like it bounces again, and so the second this hits 0, the velocity in the y direction is negative 20. What is that? Negative 29. Yeah, the velocity in the y direction starts at 29, positive up, and when it hits the ground, it's negative 29. It's the same, because there's just no, it's like it's almost like a spring, you know what I mean, with no friction. You throw a ball up, initially at 30 meters per second, it's going to land at 30 meters per second. And if it bounced elastically with no energy loss, well, guess what? It's going to bounce is going to now change instantly the direction, and now it's going to have 30 meters per second straight up, and it's just going to keep doing that. So our graph would be like, hey, it would just keep looking the same. So we need to do two things here. One, we need to get that velocity divided by 2. But the most important thing is, how the hell do we make a graph that actually bounces? Even if it does this and then does this, you know what I mean? How do we do that? And I think I can figure out how to do the graph like this. You know, and so that's the first step. Well, we, like, at this point, this term needs to be positive. You know what I mean? So let's just go 9.8. So if we did that, because that's the other thing. It's like, might as well just do something and then graph it so you can actually kind of see what's going on. So now when we graph, all right, sorry about that. So we're going to graph, and what are we graphing? You know what I mean? Oh, and last time, did we even graph the right thing? I mean, what we want is time based on y. Yeah, I apologize if I didn't graph the right thing. So we're going to come in here and insert just another time graph, because I probably caught an error there. So we're going to go 0.1, and then you take those two cells, and now you just drag it all the way down. All right, booyah. Back to the top. So now we're going to time and y. So we're going to have this graph. We'll go, yeah, we'll do the full thing, 20 seconds. And then insert scatter plot. Okay, so hell yeah. So now it did this. You know what I mean? We at least got it to skip once, but then it just went the other direction because this was positive. You know what I mean? So then if we had to do it again, we would manually come in here and figure out where the y value switched from negative to positive, which is right here. And then we would do this back to negative 9.8. And I don't mind doing this because it really just shows you, because it's not intuitive, the next step of how to actually get an equation for that. Like, I even think it's kind of remarkable. Sometimes you can't. Sometimes there is no mathematical equation, and to actually do that, you would just have to keep flipping those back and forth just to get your thing to work out. Oh man. Bummer. Okay, let's go back to the top. We have time and the y, and let's see if we have some sort of error here, but I don't think we do. Insert scatter plot. Oh, what up? What up? I don't know why it's not liking that. Oh, yeah, that got hugely messed up. That was bizarre. So whatever that is. Okay, so there we go. And so negative, so acceleration negative, so it starts negative, then goes positive, and then right here it goes negative. Cool. So now we can graph that. And we're going to insert and scatter plot. Hell yes. Now we got to go up, down, and then up. And if we just wanted this part to go in the up direction, you know what I mean? We could just say in between there is just going to be the absolute value. You know what I mean? So that's what I did right here. Absolute value of y. We could just say, hey, oh, I already have it in here. So this is the absolute value of that. And so I'm just going to drag that all the way down. And I'm just showing you kind of a few ways. Because, again, the magic trick is always the hard part to figure out. But just doing something, hey, it's not too hard. So now we're going to go that same 0.1. And now we're going to graph the absolute value, and you're just going to see, 3 kind of like frog-like jumps. So there you go, all the way down. And now we're going to insert that scatter plot. Hell yes, now we're down, 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 and then obviously it doesn't do it again because we didn't switch that. But anyway, heck yeah. Oh, and it's fascinating. The reason why there's a little bit of error here is because our time value isn't 100%. So when we flip it over, at the changes right here, hey, look at our velocity. It says it's 30.7. Well, yeah, because it's we haven't flipped this acceleration. We should have flipped this acceleration somewhere in between there. So you get a slight little variation. Okay, but what we want, we don't want to go through kind of all that hassle. So I'm just gonna take out this one just to get back to. Whoop! Did not want that. And so now we have, and even this one I'm going to delete, just so we have time, x, y, and what I want is an equation where, hey, if y is positive, this is negative, but the second y goes negative, this goes positive. And I should do this on paper, but actually it's probably better just to explain what I'm doing. So now I am gonna do an absolute value of y, and so we're gonna set that up again. And so that's real easy. We just go equals ABS, parentheses, that cell, and then we can just drag it down. And then so for this acceleration, I can say, hey, this is equal to, and now I need like so if I do this divided by this, you know what I mean? Hey, that's going to be positive 1 all the way down, right? And then I'm going to multiply by negative 9.8. Cool. Whoa. Why did I not like that? So acceleration is equal to this. Oh, it's because it's dividing by 0. Oh, damn it. No, bummer. But we can do it for we can do it for this next one. We can say acceleration is equal to this divided by this times negative 9.8. Cool, and that's 9.8. Now we can drag this down, because when y goes negative, we're going to have negative divided by positive, and then we'll get negative times a negative. And so right where that changes, so like, well, I'm just going to drag it all the way down, and then look at that. So hey, it's acceleration is negative all the way till right here. You know what I mean? Right at our, once this y term went negative, well, this is the absolute value of it. This divided by this is a negative number, negative 1, multiplied by negative 9.8, and so now we're just money. So now we can actually plot. Sorry to get rid of these. I just had to, just for my mind, else it just gets too overwhelming. 0.1. So now I'm going to do a time right here, and then we'll do the scatter plot of that. So now time and y, we're going to do a scatter plot. Insert scatter plot. Okay. Okay. Well, at least it did it. You know what I mean? Even though that this is upside down, I'm chill. You know what I mean? And I can just know that obviously it bounced and it's going that direction. So now the other thing to do is, and I haven't come up with this one. The only thing I know to do is for this velocity to just make it half. But now what I want, is there anything that happens? So right here at this point, this velocity should be half of this. But we do have something that changed. This negative sign changed from negative y to a positive y. And so the absolute values, both of these are positive. This is negative and a positive. And so if at some point we can realize that this is negative, I'm going to rack my brain to see if there's an equation that I could use to where, hey, if this is the change, if this goes negative to positive, then this goes to half. And that's it. I don't think it's actually possible, but I'll rack my brain for about 5 or 10 minutes and catch on the flip side. Alright, hell yeah. So I took 5 minutes, and there's just no humanly way to actually get this to divide by 2, and it would have to be just at this point. We would have to take this value, and so let's just at least do it once. So we're just going to say right at this point, we're going to say, hey, this value is equal to this value divided by 2. Okay, heck yeah. And now we're just we just ran the calculation. Oh, that was bizarre. Do I have to go down to here? You know what I mean? This value is equal to this value divided by 2. Or no, I probably have to go up. What was I looking at? And then let's say if I go from here, this value is this value divided by 2. So I go to 14 negative. Yeah, so that'll work. Why didn't it work right here? Maybe I was just seeing something I didn't like. Yeah, this was weird. I go from negative 14.5 meters per second downward, and then I go to negative 15. You know what I mean? So there's a little bit of a hiccup here. I don't know. I'm just going to go from here to here, even though it's just a little bit farther. So we have negative 29.984. It allows it to get all the way to that velocity, negative 29. You know, pretty close. So I just want to get a decent answer. And so there you go. So now it's got less velocity, and look, it takes considerably less time. So there you go. Between 6 to less than a second, it's going to bounce again. You know what I mean? Where this, this initial throw was, I mean, that's significant. Like, holy Toledo. I mean, if you just have oh man, I feel like there is something significantly wrong with this Excel sheet, but I can't put my finger on it, because what this says is that if we have a velocity of 14 meters per second straight up, and we're reducing that, every 1 second by 9.8, well, it seems like it would take 2 seconds to read. Yeah, am I missing something? Anyway, so let's graph this at least. Yeah, and see where we're at. Okay, so sweet. So this is our initial velocity. It bounced once, and then it has some sort of lower velocity, and then the lower velocity is the same. But from there to there, so manually we would have to do that every time. And so now what we want to do, since we have this graph, well, we will actually want to change the angle to 30. You know what I mean? We at least wanted to do that one, where our angle is 30, and so everything changes. And now we'll have a chart for that. And I guess I didn't have to delete the chart, so we're going to go back, escape, and then get the chart back. And so now that we have, and I hate how it puts the chart right at the bottom. It's absolutely insane. But now we can just change this to 30, and guess what? Our chart changed. So now, okay, our chart changed, but now it's out of whack because we have to figure out where that velocity change was. So we'll have, we're looking at the y, and where it goes negative. And what is up here? Why is this negative? Our velocity sine of the angle. Holy Toledo. I so apologize. So these numbers have been off from the beginning because, so I knew something kind of was fishy up. Just that, see how you just, you have an idea that, oh no, projectiles, they can only stay up for about 3 seconds, these projectile problems. And then I got 6. And then I just explained it away, But I guess I can throw the the triple asterisk. In my brain, I know there's something a little bit fishy. I can't figure it out. I'm just going to go on with the axioms. But Excel only does radians. So we actually need theta in radians. And so 30, so we go 30 divided by 360. 360 times 2 times pi times 2 pi. So there you go. 30 is close to 0.5 radians, and so now we have that. And so now in our calculations for this will be h3, and then this velocity will be h3. Cool. So it's like holy Toledo. So cool. We have a velocity up of 17.5, and at a 45-degree angle it should be 70%. You know what I mean? Or a 30-degree angle. Duh. It's just half of 35. So there's our check on reality, and now we're back. Okay. So now the problem should only take a couple seconds for this y term. So we're going to watch this y term, this column, and we're going to see where it goes negative. It goes negative right here. Here is our velocity in the... So now, yeah, so our velocity is downward, getting bigger and bigger. Oh, no. But we already did our cool equation for acceleration. So yeah, so now once it hits here, the acceleration switches. But at here, we want this, and we're going to go to this next one, this to be this divided by 2. So now we start over. So we went from negative 17.5, we got to negative 17.78. We can change our change in t to make it more accurate. But now we have, and this should be positive 9. But I don't have a way to, I don't think I have a way to make that happen. But now what you can see when we do graph, and then let's just simplify this. So once y comes back to positive, which is right here, we're done. You know what I mean? So there you go. Absolutely done right there. Heck yeah. And I'm just going to erase everything else. Down to 20 seconds. That's crazy. Baseball staying up for 20. I'm sorry I didn't catch my mistake, but that's all right. But no, I mean, I'm going to use that knowledge going into other problems, like where you're just like, oh, like I think something's fishy. So, but now we're just good to go, because I'm just very impressed doing these videos online, because I've pretty much caught all my mistakes at some point. Within a reasonable amount of time. Kind of like I just watch professors, and yeah, they make mistakes, but it takes them they have to go back to, looking at what they just did to catch the mistake. So here we go. So the velocity goes up, and then hits, and then it's half velocity, and then so it's going to go right here. So now we're going to have, we're going to figure out what distance x that is. And for our problem, x is in meters right here. And heck yeah, we go 175 meters. So there you go, 175 meters. Doing the double bounce. So now what we're going to do is we're just going to copy paste this one. And so I'm going to go up here. And do I have to just copy everything? I don't know. We'll find out. Yeah. No, I got to copy everything because I know what I'm going to do. So I'm going to copy this. And then I'm going to go over here and paste it in. You know what I mean? And this takes probably a long time, but we're learning more about the problem than just figuring out the answer. You know what I mean? Hey, figure out the angle. You know what I mean? And that's it. It's so dumb. Okay, so for this one, we're going to see what it's referencing. So now we need it to reference this. So we're going to go velocity is this. Dollar signs, and then cosine is this theta, dollar signs. Cool. Velocity y, kind of same thing. I'm going to do the theta first. Dollar signs. That's F4 on your keyboard. So, and I'm just going to reference this velocity, initial velocity. F4 puts dollar signs on it. So now we're just good to go. So now I can officially, hopefully, change this one to 45 degrees. Okay, heck yeah. And do I need to do anything else? I don't think on this one, well, let's just let's just graph this and see what's up. Yeah, so it's something funky. So it's where that it's where we half the velocity. So what we're going to look at is this velocity in the y. At some point we made it go half, right when y was half. So I'm going to go y. So now I'm going to look at that y graph. Once the y value went, oh no, we got something totally, you know what I mean, we got to get this one up to speed. So time is 0, meters 0, we have y absolute, velocity in the x, cool, velocity in the, cool, I'm just going to check this one more time. Yeah, so that all looks good, and yeah, that's just that. Oh, so I'm just gonna pull this crap down, you know, pull this all the way down again, and that definitely changed it. Go to my graph. Where's that? Oh, I don't know. Yeah, again, I deleted the graph, so might as well just keep the graph up. So we're gonna go, oh, I can just click here for charts. Sweet. Yeah, I don't know what, so yeah, something's funky right there too. What is it? And where is that? Like 1.5 seconds? What do we got going on? Oh, something right here. Oh, look at that. So this, there we go. So now I can just, I'm just gonna pull all this stuff down again. I don't want to ruin my absolute value equation. Oh, but for this one, I was thinking okay, so we're just gonna pull all this stuff down. It kind of resets everything. Didn't get rid of this. What is up going? You know, what's going on right here? Yeah, what is it referencing? Oh, it's the time frame. Cool. So yeah, the time frame is off. There we go. All right, caught our error, but that was brutal. That was brutal. Okay, hell yeah. So now we're just good to go. And why is it starting here at 0? And why is that all funky? So let's go back up to 0. Yeah, what the hell's up with this? You know what I mean? So acceleration in the y. Well, duh, acceleration in the dx should be 0 the entire way. So why isn't it 0? Because we got this. Okay, so here's the other thing. Yeah, acceleration in the x has to be 0 all the way down. Okay, and we still got something funky going on right at the beginning. Let's get this graph up here, though. See, I don't like this where you can't drag graphs very fast. Absolute insanity. Yeah, so what's going on at the beginning? Oh, well, maybe this time frame is all out of whack. You know what I mean? The actual time frame that we're actually using to chart the darn thing. There we go, 5.8, 5.8. Perfect. Okay, so that took a while. Holy hell. But now we know everything's perfectly fine. So that is the troubleshooting part of Excel, is like, yeah, one thing gets off, the whole thing gets off, and you got to figure out how to troubleshoot. Okay, so now right down here, oh, so now what we're going to do is where the y-axis goes negative, and that's it, because there is no bounce on a 45. You know, that's the whole problem statement. So right where that goes negative, that happens right here. So I'm just going to do right where it went negative, and just a little after that, and so we got 126. So there you go, 126 meters. And this one only went and then this one went 175. So this one's going way farther. You know what I mean? So a 30-degree angle. So what we want is on one bounce for it to go only 126. So there you go. So what we're going to do is maybe reduce this to 20 degrees. And no, we'll just do 25, because I kind of know this problem does have the answer in the back of the book. It's like 26 something, because this one just sucks, because there is no fancy way. You do have to make it, you have to manually manipulate it. So even right here, we're going to have to figure out where it goes negative on the y-axis. And I might have to drag down this velocity in the y so it's not changed. Yeah, see how that changes it? So we have to refresh that. We have to see where the x goes negative. It goes negative right here, and then our velocity in the y is this one, I thought. Yeah. So here's our velocity in the y. Here's our y. So where that goes negative, this is where we have to half that velocity. So we're going to go that divided by 2. And there you go. So now we'll get a distance. So now we're going to see where it crosses the y-axis one more time. And that's going to happen right here at 161. So 161 meters. This one went 126 meters. Damn it. I feel like they're not going to converge. But that was 20 degrees. Oh, this is interesting. And yeah, speed's the same, 35. So I guess I'm going to change this to 20 degrees. I'm going to reset my velocity in the y. I'm going to see where it crosses the y-axis. And then I'm going to spot for errors if the answer's not close to the back of the book. So right here is where I'm going to change my velocity from this divided by 2. Cool. My acceleration looks good for that. And now I can... that's what it's going to look like. And then we have a distance. Well, now we need to see where it crosses the y-axis twice. So here it crossed the first time, and then we divided the velocity by 2. It's negative, and the second it goes positive. We're at 124. So there you go. There you go. 124. And I just kind of maybe forgot the answer in the back of the book. You know what I mean? So again, it's crazy doing these problems because there's so much bias in your head because there's so many places to generate error. So this one is 126. Now on this bounce, when we did a 20-degree angle, it's going to hit the ground pretty fast, and the velocity is going to go half. And this isn't, that's not what we're looking at, because every time we're going to have to look at a different number. And right here is where this went. So now right there is our value, 124. And we compare that to 126. So now let's just up the degrees by 2. So we're going to go 22 degrees. And we have to reset our velocity in the y. See, that's the bummer. That's why it would be cool to have an equation that just, manually does that. Where if I just click this, it's going to reset the velocity in the y. And then it's going to manually, I would love to set up computer program. That would be the first thing I'd want to learn with computer programs, is like how to do that kind of stuff. So we're going to look at where that and these two, where the y goes negative, happens right here. So I'm going to say this is equal to that divided by 2. And then I'm just going to watch where this y goes negative one more time. It changes again. So it changes right here at 142. So that was a huge difference. You know what I mean? And my graph isn't the best. And so I'm actually going to take a pause. Alright, hell yeah. So the answer in the back of the book is 26.6 degrees. And so now we just need to double check everything. So this is degrees divided by 360 times 2 pi. Cool. And that was already legit. And this one was going to be 45 degrees. And we're just assuming some velocity. You know what I mean? And we can just say, no. We'll keep it at 35. I mean, I think that's decent. Because that's be pretty decent. But we just need to, the crazy thing is so let's do that. It's like, where is our error? Because if we did that, we're going to reset our velocity. So this is going to be the original plus our change. Because it feels like we have an error somewhere. Okay, so once we did that, we're going to see where the ball hits the ground. Hits the ground right here. And so that's where this velocity goes from negative 14.7 divided by 2. So now that velocity is 7.35. Just to check on reality, this velocity started at 15.6. Got back up to... so that's where I should change it right here. Divided by 2. Make sure it goes back up to 15.6 and then switches. You know what I mean? So that's where I was maybe getting a little bit of a clerical error on this side for my chart. And so now, but everything looks good. Half velocity comes back up. We're going to see where it crosses the y-axis again. And that's going to happen at 159. Okay, so now we're in. You know what I mean? I think that made a big difference. And it's always good to see what things cause error. So I'm going to go back to Control Z, and I'm going to do this divided by 2. Whoa. Oh, sorry. No. Equals this divided by 2. And then it shifted it. So it ain't going to go very far this way. So what this says is, no, we're back. So I don't know if an error just came out of the wash, but I'm going to go Control Z, Control Y. Let's see. Bummer. I don't trust myself. So we're going to bring that velocity all the way down. And where the y-axis, where the ball hits the ground is right here. I'm going to allow it to get up to 15.6. And then I'm going to take this value as that divided by 2. Cool. And now I'm going to see where it hits the ground again, which is right here. And we have 159. So now I can just highlight that. Okay. And so this should equal the value I would get over here. But yeah, that's where I was just like, nah, this went a farther distance. You know what I mean? Because in the problem, they're saying, hey, at what angle does it go the same distance? So we just did, Excel. I mean, in Excel, we just did projectile, trajectory for that. And it's just not getting the same answers. So, I feel like that's not a good check on reality, and I feel like there might be errors. And the error is probably over on this side, because we just copy-pasted this. So we're going to do our time frame again, 0 to 5.8, and just check to see over here, see if that time frame is the same, 0 to 5.8. Alright, x is 0, y, absolute value, so we're all good there. This all looks good. The y is the sine component. This is the cosine component. Yeah, so we're looking good there. Acceleration in the x is always 0. I'm just going to check that. Looks good. Acceleration in the y is always negative 9.8, except when it crosses... Oh, and in this case, yeah, this might be No. This is good. Where it crosses is where it crosses, and that's 126 meters. So we're good here. And I don't even need this part of the graph. Well, let's at least run it a couple. I'm gonna leave it. I'm gonna leave this in just because the last values are you know, these are wrong values because they're trying to take these values and those are 0. Okay, so yeah, and our change in velocity in the y, that's negative 9.8 because our change in time is a tenth of a second. So that all looks good. Except when it's, you know, the other direction, positive. So now the velocity average, just those two divided by 2, so that looks good. I'm just going to drag that down. Nope, good there. Velocity y average, cool. And then dx is velocity average times the change in time, dy. Velocity in the y average times the change in time. And yeah, bring these down. Yeah, nothing changed there. So we're good there. And now our x is going to be, hey, the initial x plus the change in x. Cool, good there. Our y is going to be the initial y plus the change in y. Good there. And then the absolute values, those two columns are the same. So yeah, these two columns are identical. And so with a 45-degree angle, with no bounce, this ball goes a distance of 126 meters. But in this case, if we do a bounce with the answer in the back of the book of 26.6 degrees, we get a farther distance. By the time it bounces and then hits the ground again, it's already at 159. So maybe, like, I feel like I'm misrepresenting the problem or something, because what they're saying is that the time that it takes both throws to get there should be the same, because this part goes slower, and we already did a very good job of taking that velocity and at that point dividing it by 2. And it says that just the ball speed after it bounces is 1/2 of what it was before the bounce. And it doesn't say the x component is 1/2. You know what I mean? That would be kind of bizarre. But it just says the ball speed after the bounce is 1/2. And yeah, determine the angle the fielder should throw the ball to make it go the same distance with one bounce, the blue path. Yeah. So again, we can maybe look through our errors on this side. We have this time. I mean, we already do that. So this is 5.8. This is 5.8. So that all looks good. So the time frames are right. The acceleration is negative 9.8 unless it switches, and then it's positive 9.8, and then it switches again, negative 9.8. So that looks good. Acceleration in the x is 0. That makes dvx all 0. Change in velocity in the y is negative 9.8, except when it switches. Oh, so like even just right here, this might make just a little bit of a hiccup. So I'm just going to manually set this as negative. And did that change? No, that doesn't change anything. Oh, interesting. Yep, because if this is the acceleration, then here's my dv, and so we're already saying that the ball has a velocity downward, but we're trying to kind of reverse the situation. So now the velocity's up, and so whoa. So this term is just that. Yeah, am I messing up somewhere? No, because this term is based on that term. Cool. And then we just manually put this term in. You know what I mean? And I don't think that messes anything up, because now we have that term as our, and then we should have our velocity average. Oh, that's what it is. Holy Toledo. Okay, I apologize. So we did catch the error. You know what I mean? Because literally our equation says at this point, and I guess I'm just going to highlight both this changeover. So yeah, that was the crummy part. But there you go. We found our error, and it's because of this velocity average term. You know what I mean? We can't, you know, once we start the problem over, it becomes kind of two separate problems. Where this first problem, you know, got 100 meters. You know what I mean? Cool. That's it. You know what I mean? So we could just say, hey, that's equal to, you know, 100. And then the next problem says, well, let's say if we have a velocity with half that, 7.8, you know, how far would we get? And so right here, I wish there was a way to, so R and S are the velocity averages. And so right here, the equation for this is that one looks fine, but the equation for this one, yeah, no, this one's wrecked. So this average velocity at this point, because this is our change in velocity. So yeah, that is a bizarre thing. Like, let's say we just started out with 7.84. Yeah, even right here, we're, oh yeah, so yeah, it is a bummer. You know what? I think we can finagle it. But let's say our velocity right here is accurate. And so this is the change in velocity. Cool, those look right. This one is the change in those two velocities. That looks right. This one is the change in those two, the average between those two velocities. That looks right. And then so for this one, I just have to also say, just for the life of me, I'm just going to say that is equal to this velocity. So now that's going to be the velocity average at that point. How do you do the velocity average right off the get-go? This velocity average is going to be that plus the next one. So yeah, maybe I could figure it out. So I'm just going to say that this one velocity, so this velocity average is that one plus the next one. This velocity average it should just be this one plus the next one. Oh, it was this one that was messed up anyway. So this velocity average is 15.6. So I apologize. So we're going to go back this one. It's this one that is the messed up one. This is just, I'm just going to say the velocity average is that and call it. And heck yeah. And then that's going to cause so now our change in the y is just negative 5.6. But even, you know, are we taking that too soon? Because even just like right here, we're starting the problem over where we shouldn't have, yes. So, but anyway, did that change it just a little bit? Not really. Okay, so now what I'm going to do You know what I mean? And it is just the troubleshooting process. But because you have these, we can just do 3 of them. So I'm just going to copy this one, grab a new sheet, paste it, and so we have our velocity is going to be, oh, and yeah, so I think all the numbers are just totally messed up now. No, we're decent. Yeah, it's oh, this is good on me to like actually just do this right up against, so if I do copy paste it, you have to copy paste it in the same location. All right, but yeah, we'll suffer through this one. So our theta right here is that theta, F4. Cool. And then our velocity in the x, our theta is that theta. This term for our velocity is just our initial velocity, F4. Oh, and this one I gotta do F4. But yeah, this is the part where you kind of lose your mind, where you're just like, damn, I'm kind of tired of this, and we made a couple errors. But this is kind of where you got to stay probably more. See, and I'm not even more focused. Is equal to that, F4. Making sure you got good checks on reality, 45-degree angles, both of those are the same, negative 9.8. Changes look good. Velocity average looks good. Yeah, so everything looks good. Here's where it crosses the axis. And so we're good there. I'm just gonna get rid of those two. And this says 126. No, yeah, so yeah, 120. I don't know why. For the life of me, I can't find why the answer in the back of the book isn't what I'm getting. You know what I mean? I'm thinking it's a continuity thing. Okay, so we did it. This one should be good to go. Yeah, velocity average, meters per second, times time is the distance. Yep, so we're good there. Yep, good there. And yeah, I guess we'll just graph this one. Cool. And we're just going to copy this whole thing. So now when we copy a new sheet, so I'm just learning like, yeah, how do I do this faster? So now we're going to go 30 degrees. I just thought I had a clever way to set it up in Excel, but no, that was a total nightmare. So now what we'll do is we'll do 2 separate graphs. So where this crosses the y-axis, or where it is where it hits the ground, and that's going to happen basically kind of right here. So we have, so right there, it for sure crosses, so at 109, maybe just a little bit less. And let's get rid of this. And now we'll set up a second problem. So we're going to copy this and then paste it in. So I'm going to say this is 45 and this is 30, but the first part. And this is 30, but like the second bounce. Whoops. Okay, so now right here is what we want to figure out. What was the velocity? Oh, and this is going to be real simple, because on the second bounce, I mean, the velocity where it started at 17.5 is the same velocity that it ended with. And so when we go to the second problem, we can just say, hey, this velocity is equal to, and we can go back to this sheet, this velocity, come back to this sheet, divided by 2. Oh crap, I did not like that. So this is sheet, this should be half, so we're going to say, hey, this is equal to this velocity. Whoa, why isn't it liking going between sheets? Alright, well, screw it. This is just 35 divided by 2. Alright, hell yeah. And now in the y, and that's the thing. The second you start running into errors, from the get-go, I should have just kind of made it simpler instead of trying to very tactfully. But we were just kind of learning a different way. But we saw the errors. So there you go. I'm just going to go down a couple. And so this is going to cross right there. So that's going to be at 27. So now we'll have 27. And why doesn't it like this? 27 plus, why can't I go to another sheet? Oh, I see why. 27 plus this, go back to this sheet, and then enter. What the hell? I don't know why I'm having problems where I can't, add it to this number from a different sheet. Oh, I guess I'm sorry. I'm just gonna copy this. No, I don't think I'm gonna do anything. So I'm just gonna get out my calculator. So we have 27.3 plus 109.1. It's 136.4. Because we were just trying to figure out if this problem is right. Oh, and we already kind of messed up. Answer in the back of the book is 26.6. So there you go for that angle. And then this one, home. See, that's where it's just like, you know what I mean? Getting lost in like the details. And so this is going to cross the axis right at this number. And this one is going to cross, let's get rid of this, is going to cross right here. So we have 100 plus 100 plus 25, 125, which is, yeah, so we're good to go. And then this one is 126. So holy Toledo. So there was something just messed up with the way that I did it. And that was a bummer. But I am going to go back and figure out why and how I could have changed it to be better. But yeah. And so there you go. So we have that relationship, and it works out. And I already had the answer in the back of the book, and so we kind of just cheated and went there. And so I'm gonna at least spend just a couple. I'm going to take this to at least like 4 seconds. I'm going to bring all this stuff down. And so this has to be 0. That's the only one that got messed up. So yeah, so I think we're good there. And then I'm going to bring this down. And this is far enough. But if we were playing around with this, if we set this angle at 45, I'm sorry, this has got to be 35. If we set this angle at 45, and then this angle at 45, we would find from the first one where it hits the ground. How many seconds is the first one? Holy, yeah, I guess it is. It's a 5-second problem. So it hits the ground at 5.2. Bummer. I thought I pulled these down far enough. I'm going to get this graph out of the way, and then we'll go down, get this graph out of the way. 3.6, 3.89. Yep, there we go. Alright, and then just in Excel, stuff like this kind of pops up where you just got to fix it. Okay, so I should have done it just the simple way all along, but you know, both these angles are now 45. And so the first graph says, yeah. And so the first one, the second one should have a speed of 17.5. Cool, it is. So this graph will hit at where this went negative, 126. So in my calculator, 126. And then we add it to the other one, where it hits the ground. The second bounce has half the velocity, and it's going to hit the ground at way up there. It's going to hit the It's going to hit the ground right here at 32. That's significant. That if your velocity is 35, like 35 meters per second, and you're throwing at a 45-degree angle, you can go 60 meters. That's amazing. But then you half that. If you only threw at half the speed, holy hell. You know what I mean? So that's kind of the take-home point there. You're only going 32. So now we have a total of 158 for that. And we know back here that if we just throw once at 45, we're only going 126. So then what we do is we need to reduce the angle. So then, I would just do 30. And so that was the whole problem of just like, that was the whole thing. Get it in Excel and then just play around with it. I just thought I had a creative way to play around with it. And obviously I totally struck out. It's a good learning deal where you're just like, whoa, we just spent maybe an hour more trying to dial something more specific in, where we could have just done this, and we wouldn't have had to done any of the absolute value stuff. I mean, we learned a little bit of how you can do that, but it was just a hiccup with that velocity average once it switched and you had to do it with half. That did not work out. Okay, so now where it changes, if we have 30 degrees at half, I guess I'm doing the second part first. Where it crosses is right here, so we're only going to be able to add, let's say, 27. And then we'll go to this one. So at 30 degrees, where is it going to cross the y-axis or hit the ground again? And, not the y-axis. I got to catch myself when I just say stuff like that. This is the position in the y direction. So it's on the ground, got thrown up, 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 and then where the y value is 0 is it hits the ground again. That's where it does cross the x-axis. You know what I mean? So then we got 109. So 27 plus 109, and we got 136. Go back to this is like, no, we're in the same. We're going. Not anything is based on time. Going back to the first thing, the problem just says, hey, the continuity that we want to solve for is that at 45-degree angle, we're going to go this distance. But if we reduce the angle with that same velocity and then it halves, our ball is going to go the same distance. So we just found that at 30 degrees it went farther. It went 136 meters, and this one only went 126. So then you would reduce these angles yet again, and we can do a shallow angle of 20. You're kind of using the Price is Right method of mountain climbing. But if you do this, you learn quite a bit. So the first one is this y. We have 20 degrees. It's going to hit pretty soon. And so we hit at 82, let's say. So 82 plus, and then the second bounce, we only have half that velocity. Where it hits the y is at 21. So we have 82 plus 21, 103. So now we're undershot. So now we would go to like 25 and see if we get close. And that'll be kind of the last one. And hopefully we do get close at 25. And even that would be enough to confidently say, we were accurate. But this problem really showed us, like, do not get complex. The only reason I got complex is because I kind of knew the answer in the back of the book. I had that to reference. I had plenty of things to reference. But if you don't have the answer in the back of the book, you're just bound to make huge errors where just making the problem simpler is the way to go. Just getting fast answers and then dialing it in. Getting your first answers to be kind of rough estimates, but then have a high degree of accuracy. All right, so this is going to be 98. Let's say 98 plus, and it might be just a little bit less. 98 plus 25, and we get like 123. Okay, and this one was 126. So now we're too low. We have too low of an angle at 25. And the answer in the back of the book is 26.6. So there you go. I hope to finish this problem with the actual proof. But for my point, for this video maybe, I think I might be done. And so thanks for joining me. You know what I mean? But now this gives me a good representation of what's going on. And no, I'll probably add to this because the time frame is what I was most interested in. It was just like, well, how long? And let's do that. So let's do this 26.6 because that was the whole thing. Is I had no idea the ratio between the first bounce and the second bounce. That's where I was kind of messed up in finding my continuity equations. So now for the first bounce, where it's going to hit is going to be at time like 3 point. Yeah, I would definitely say 3.2. So we got 3.2 seconds for that first bounce. The second bounce will happen in 1.6 plus 1.6. So the whole thing on the first throw should be 4.8 seconds. Or is that true? Is that true that the distances are the same and then the time in the air is the same? No, it's not. The time in the air for the first one is 5.1 seconds. And so what we're showing is that with it's kind of a bizarre thing, and I'm sure it gets explained in that second part of the problem is like, what is the ratio? At what point do you not want to do a one bounce throw? And it's just like I don't understand that unless every time it hits the ground it's reducing its velocity by half. That's the only thing that I can think, because with the single bounce it's going to take 5.1 seconds, and so it takes longer to do the first throw, where we can go, and that's what they're saying. It's like we can go the same distance in a shorter amount of time. And that's kind of why I was having a hard time with the continuity, because the time frame to do this sweeping arc is obviously longer, and that's what they're getting at. That's the whole problem. Is like, hey, if you do a double bounce, even if it slows down on the second bounce, it's going to get that same distance faster. Alright, so hell yeah. So at least, I mean, that was the whole thing. You know what I mean? Let's say I never actually figure out how to set up the equations to solve this. Like, I don't care. You know what I mean? That part is useful to actually figure out how, like, the axioms are put together, and I might go over that at the end of this, or maybe have that at the beginning of this video. But we'll see how I do this one. But just throwing in Excel, I at least found a way to get an idea of what's happening with this problem. And I have more to play around with in Excel than I do an equation that I can't get. You know what I mean? I can't get the equation. I don't know the magic tricks involved. But from this perspective, I can now, have target values. Because okay, yeah, so let's continue on with this thought. Because now I know the time frame it's going to take the ball go from here to there. It's going to take 5.1 seconds. And in this one, it was going to be 3.2 plus 1.6. So hopefully I can remember that. So now, and going back to the original picture, is so it's 3.2 for this one, and then 1.6. And then because the question that I had was like, well, if that's the case, what's this distance right here? And we already found it, you know what I mean? So from Excel, we found that was 100. And this one was 25, like 100 and 125. Let's say that. And let's say this is just at 120. Yeah, so let's say it's 125. So we have 100, 25, and then just the full throw is 125 to get there. We have a time value of 3.2 seconds, and then 1.6, and then a time value of 1.1 to do the sweeping arc. And it was just like this. That's all I wanted. Was just this. And it was just really difficult that I couldn't figure out this relationship due to the. I mean, this falls out of the equations when you put them together, but I just wanted to have an idea of where it would happen. So now I guess my question is, what is this? What is the percentage of the distance? And it's so fascinating. Like even right now, it's like a head scratcher for me, even though it's just now it's all obvious. So this distance is 125. This distance for the first throw is 100, and this part is 25. So we have 125 divided by 25 is 5. We have 5 equal parts. We have 4/5 for this first bounce, and then 1/5 for the second bounce. So that really explains this problem. That once this velocity reduces by half, like holy Toledo, its ability to hop another distance is incredibly reduced, and it makes sense. With the initial velocity, we can go 4 times the distance, and then when that velocity is reduced by half, we can only go a quarter of the distance. So let me say that again. So when the velocity is normal, we can go 4 times the distance, and then when we half the velocity, because it's a velocity squared, you know what I mean? You half the velocity, that's 1/2, and then you square that. So if we go, what's the 1/2 squared? You know what I mean? Well, that's going to be 1 squared, and then divided by 2 squared. So it's going to be 1 divided by 4, and we get 1/4, not January, but you get it. So that was a fascinating, and so that's so fascinating now that even just after running in Excel, I have more of an idea of what's happening. Well, if I got the answer right, I could do the same calculation, but it's just fascinating that running it in Excel, I'm probably going to do this mentally more to try to figure out more about this problem. So 4/5 the distance, and then 1/5 the distance to get to that same location. And so now I'm curious. I'm curious of what they mean by determine the ratio for the times of one bounce, for the one bounce and no bounce throws. Now I'm just throwing something out there. Are they saying that if your angle is less than 26.6, you should? I mean, because let's say you just had to get to this distance. I mean, wouldn't you throw at a sharper angle? Like, wouldn't this be your initial question? And then you're like, well, can't I throw at the same speed but a lower angle and have it bounce twice? I think that problem exists as well. So the second problem is bizarre. I don't really understand what they're saying, and the ratio is 0.994. Determine the ratio of the times for the one bounce throw, like always, and then the no bounce throw is And the other thing to do is this distance is 125, so we can use that answer in the back of the book to be like, hey, what's 0.994 of 125? It's 124.25. Yeah, I don't know. I'm gonna play around with that one. And also the concept of a 3 bounce throw, just to figure out what they're doing. But okay, so I think I have enough to go on this, and I have enough to actually have more information when I actually run the calculations through to actually try to get the right answer. So we'll see if we do that right now. But anyway, on this part, thanks for joining me, and that's a video. All right, hell yeah. So embarrassing, because that question that said, what is the ratio, determine the ratio of times for the 1 bounce and no bounce throws. Like, I didn't understand the question, but no, it's the ratio of, like, hey, find the time for the 1 bounce throw that you found, like the time it took for there, which was the 3.2 plus 1.6, you know, from Excel, and then the time for the no bounce throw, that took 5.2. So we basically have a ratio of 4.8 divided by 5.2. That was 0.293, and the back of the book was 0.949. You know what I mean? So obviously in Excel, your answers aren't 100%, but we can, you know what I mean, in Excel, if you wanted them to be 100%, like here's, and we'll go over this, like all you have to do is know that we have to go to 5 seconds, so you're just going to take this 0.01, you know what I mean, and you could even go 0.001, but now to get to 5 seconds, like heck yeah, you got to get 5 times the distance down there. Okay, booyah, we did that. And so now for all this stuff, we have to, let's get rid of this, and whoa. And so now we're gonna pull all this stuff down and then just kind of check it for errors. Okay, so page down. So it's this one. This 0's got to get pulled all the way down. Heck yeah. And are we getting the same value? Here's the y. And we're going to see where that y goes to 0, and that's where it hits the ground, and it should be at 125. So cool. And this took 5.06 seconds. So now you can see our accuracy is somewhere between 5.05 and 5.6. So now we're just going to say 5.06. I'm going to write that down, 5.06. So now we can do the same thing for our other two, and let's do it, you know what I mean? So we're just going to go 0 to 0.01, and we're going to get a very accurate answer. Pull it down to, there you go, good enough. Pull these down. Make this 0 all the way down. That's the only one that kind of got messed up, so that's good to know. Okay, now we should just be good to go. And so we're going to do this column where this hits 0. Holy Toledo. Okay, it's going up, coming down, hit 0. Okay, so right here is 3.2. So that one's pretty darn accurate, 3.2. So we have 5.06 and then 3.2 for this one. Yeah, that's really accurate at 3.2. Cool. So now this one, 0.01, and we'll make this. This is the second bounce part, so we're going to make this accurate. And let's see how to navigate Excel. So if I put here and go Control Up, goes to there, and then Control Up, goes to the top again. And then from here, I don't know, I'm just going to have to page down until I get to this value, turn this to 0, all the way down. And heck yeah, so it's where, and we'll go all the way up, because we want this where it goes to 0. It happens pretty fast. Well, no, we go up, and then we go down. So right here at 1 point, oh, this one is really accurate. You know what I mean? So it was that other one that I was just off on. And I bet you if I go back, I made an error. Actually, I thought I just guessed 5.2. I'm sure it wasn't. Whoops. So this one is 1.6. So we have 3.2 plus 1.6 is that 4.8, and we're going to divide it by 5.06. So now we get a ratio of 0.949. So now I get the official ratio, and then we answered that question in the back of the book. Alright, so hell yeah. So now I'm going to make this a long video, and now we're going to actually just suffer through the actual calculations to get the actual equations and to see what's related. Alright, so catch you back in writing. Alright, hell yeah. So we're back from Excel, and I want to hunker down and do this one. And I'm not going to show you the picture no more. We've seen it. And hopefully, once I get this done, at the beginning of the video, I'll just walk through it, you know what I mean, in a short amount of time. So that initial one goes up like that, the other one goes like that. And so we have initial velocity, we have a velocity, anyway. So let's, yeah, maybe I'll go faster through this, just because I want to get up to the point where the continuity doesn't work out for me. And then so we have, hell yeah, this distance is d. So acceleration in the y is negative 9.8. So everything from Excel is the same. And acceleration in the x is 0. And then when we integrate, we kind of want to integrate these. And how you do that is, well, acceleration in the y is, just acceleration in general is dv dt. And so we want to separate variables. Because this acceleration, you know what I mean, I've always done this, like, is a function of time to the 0. You know what I mean? It's also a function of x to the 0. You know, it's not a function of either one, but when we do separate variables and get this dt up here, so then this becomes dv is equal to a dt. And so that's how we get dv is equal to negative 9.8 dt, and then we can integrate. And then so we get an equation for velocity. It's going to be negative 9.8. T to the 0 goes from t to the 0 plus 1, 0 plus 1. That's the integration, you know what I mean? So this is t. Anyway, and so you get, so a constant integrates to negative 9.8 t plus a constant. Now, and I'll just write it in. And then when time is 0, well, we want to know what the velocity is. You know, and now we're just focused on the y direction. Velocity in the y, and this would be the velocity in the x initial. And so, and this equation basically is a velocity in the y, because we're trying to find the acceleration. Change, you know, so we have kind of two equations to do this. And then let's do the other one in the x. So we would have acceleration in the x is dvx dt. And if you don't like that, just acceleration in general is change in velocity, change in time. Then put acceleration as dv dt. It just makes it, and you can still say the same words, change in velocity, change in time. Cool. Now, you know, separate variables, and we get dvx is equal to ax dt. Integrate, we get vx is equal to axt. You know what I mean? Pretty straightforward, plus a constant. So for this one, if our time is 0, this goes to 0. So our velocity in the y, well, this is just our initial velocity initial. I'm just going to say is v. So that's just going to be so our velocity in the y is going to be v. And if here's our angle, you know, of like 45 or whatever, this velocity. Sun is shining on the sine end. So we have the bigger number, the hypotenuse, times the sine of 45. Hell yeah. So we got Vy is equal to negative 9.8 t plus V initial. I'm just going to, yeah, I just don't like how the letters just get too crazy. But V initial, sine, and for now I'm just going to write, no, for this one I'm going to write sine 45, because we're going to have, like, now a bunch of equations. You know what I mean? We're going to have two equations for this first projectile, and then we're going to have two more for the second one, because the second one is going to be just a angle theta. We don't know. So the velocity in the x direction. When time is 0, velocity in the x is going to be, the constant is v initial cosine 45. You know, that's the velocity in the x. Alright, hell yeah. So now we have these two equations, and then we can say velocity is equal to change in position, change in time, is equal to dx dt. We can separate variables. Velocity, you know what I mean? And, velocity definitely, visibly is a function of time. This is t to the 1. So we're going to say that this is, so Vx is equal to dx dt. That's literally saying, hey, write this equation. This is Vx. So we got axt plus vi cosine 45 is equal to dx dt. So now we can bring the dt upstairs. And cool, it looks like we're going to be able to integrate that. And then we have the dx over here. And I should pause and actually figure out what the hell, you know, that hand waving even means, but I might just have to move on. So now this is, I'll switch it around though. dx is equal to axt plus v initial cosine 45 dt, integrate, and so now we have an equation for x is equal to axt squared, and then it's 1/2. Because this is t to the 1, so you go t to the 1 plus 1 divided by 1 plus 1. You know, I need to write this every time so I just don't forget, you know, some basic integration. All right, now plus vi cosine 45. There is no t on this. T to the 0 goes to 0 plus 1 divided by 0 plus 1. Cool, and we got t to the 1. And then plus a constant. And then so even here, when time's 0, these both go to 0. What's our position? Well, our position is 0, because we're saying this is x, this is y, this is the origin, 0, 0. So cool, that is our equation for x. Now we want our, oh, and I totally apologize. See, we just already messed up. This is vy. So this is vy, dy dt, dy dt, dy. So this is an equation for y. Now if we do the one for yep. Oh. Yeah, holy hell. And we messed up here. Obviously, acceleration in x is 0. So wherever I wrote that, you know what I mean? So this Vx equation is 0 times t. So this is just vi cosine 45. Oh, okay. So yeah, and then oh no, this was x. I apologize. Holy Toledo. But yeah, this is just 0 anyway. So that term is just absolutely out of there. So even though we have a formal way of like, hey, if that was something, it would look like this. But if that term is 0, you know, our y is just v initial cosine 45t. All right, and so that, no, I'm sorry, this is the equation, the x, my apologies. And yeah. So this is our equation for y. If we do that same thing and say dvy dt is equal to negative 9.8t plus vi sine 45, and then separate variables, integrate, we get, oh, and what am I doing? I'm saying Vy is equal to dy. There you go. So this is Vy is equal to change in position, change in time. You know, and so this derivative is equal to, you know, basically just the velocity function. And so now we can separate variables and get y. So sorry, that was just really haggard, but I'm just trying to get to the part that I don't know, since this video is just hella long. So we have negative 9.8t squared divided by 2 plus v initial sine 45t. So here's our equation for y. Here's our equation for x. And I think we can just get a new sheet of paper. So we're going to have so v equation for Vx is, where was that? Isn't that just, oh yeah, just V Yeah, it's just a constant. You know what I mean? The velocity in the x direction is a constant. Cool. VI cosine 45. Now the velocity in the y is VI sine 45. Oh, shoot. I'm just trying to guess on this. No. The velocity in the y is negative 9.8 t plus VI sine 45. That's it. And then so we have position in the x is going to be VI cosine 45t. Position in the y is going to be negative 4.9. That's 9.8 divided by 2. And 4.9 t squared plus v initial sine 45t. Alright, so I think I'm satisfied there, even though I just wrote them just ugly. Now for this one, for that first, so we have, so we have the lobbing shot, and then we have what it kind of looks like is 4/5 from our Excel graph, and then it's a second bounce right there. So this is what we're going to see. We got an equation for that. We got our two equations. So this one is basically going to be the same as all these. So I'm going to go Vx, and I'm just going to do prime is equal to V initial, but it's cosine theta. And then we have Vy prime is negative 9.8 t plus V initial sine theta. And then we have y prime is equal to negative 4.9 t squared plus V initial sine theta t. And then we have x prime is equal to V initial cosine theta t. Alright. And cool. And then for this part, the second bounce, our velocity x double prime is going to be 1/2 V initial cosine theta. It's basically just the V initial divided by 2. So, and then everywhere we have V initial, it's just going to be V initial divided by 2. So we have Vy double prime is equal to negative 9.8 t plus 1/2 V initial sine theta, and then we have x double prime is 1/2 V initial cosine theta t. Y double prime is negative 4.9 t squared plus 1/2 V initial sine theta t. Alright, hell yeah. And it just seemed, at this point, it's like I just kind of gave up. It seems too busy. And I had no idea. And so this distance is d. And one way to find d, I thought was just like, oh, well, that's easy. It's just the time. So whatever time for the lobbing shot, going up and then hitting the ground, whatever time value that was, I'm just going to take that time and then multiply it. So if this is in seconds, and I want to get distance in meters, but let's say I just know the velocity in the x direction. That's in meters per second. So how do I take meters per second and seconds and get meters? You know what I mean? Hey, I just kind of multiply. And so we're going to take the time multiplied by the velocity in the x for the lobbing shot, and that's going to get us that distance. So that was the first thing that I did. And the time for the lobbing shot to go up and down is when y is equal to 0. So the position y is equal to 0 right there. So this is the y positive. This is x positive. When y is 0, it's on the ground. When y is 0, it's on the ground. That's why you have a x squared equation, and it's an easy one. And let's go to this one right here. And so for our initial lobbing shot, it's y is negative 4.9 t squared plus v initial sine 45 t. You know what I mean? And what you can do is just factor out a t, and you do this. You go negative 4.9. Now we just have 1t plus vi sine 45. So now and we're trying to find when this is 0. And so we have two separate equations, because anytime that you have a product, if I throw in 0 here, hell yeah, that's 0. If I throw in 0 here, hell yeah, this is 0. It doesn't matter what this is. If that is 0, the whole thing's 0. So you get two equations that say time is equal to 0, like t is equal to 0, and then you get this. Then you get negative 4.9 t plus v initial sine 45 is also equal to 0. You're like, this has to be 0 or this has to equal 0. So now we bring that over there, and I'll just do that like this. So we get 4.9t. The negative sign goes away because we brought it over there, and then we'll divide this by 4.9. Hell yes, now we get t. So we got a value for time is v initial sine 45 divided by 4.9. And like I said, if we had time, we can just multiply it by the velocity in the x and get the distance. So we're going to say distance is time, and we already found this time. And this time is kind of like time final. I'm just gonna call it t for now, because we're going to get two values of time. So this one is going to have a value of time that gets you there, and then this value will get you there. And we've already solved the problem where this time is not. So like let's say this is t prime to get to there, and this is t double prime to get to there. Well, that is less than just the t that we just solved for to get there. There is no continuity there, and that's where I kind of made my first mistake of just like, well, is this problem saying it's going to take the same amount of time? No, it's a cool trick for baseball that you can get there faster. Faster there means that you're going to get more outs more often. So it's a pretty cool physics problem for the MLB baseball. All right, so let's solve this d. We said that's going to be time times the velocity of x, and we just solved for that. So d is equal to v initial, this is our time component, divided by 4.9, times the velocity of x. Well, that's times v initial cosine 45. All right, hell yeah. So now we don't have anything that's super nice, but we have d is equal to v initial squared sine 45 cosine 45, and I'm sure there's some sort of little trick you can do to simplify that or something, make it more reasonable. But okay, so now we have a distance d, because the only continuity that I see is that this has to reach distance d, and then these two arc lengths have to reach distance d. And so I think I kind of wanted to have an initial parameter here, maybe like, hey, this is A. This is point A, this is 0. This maybe is point B. That now I have an equation that says, hey, the distance, like OA, that distance, magnitude of that distance, plus AB, magnitude of that distance is actually D. So that's another equation. This plus that has to equal D. But yeah, this is kind of where I was getting a little bit stumped of like, okay, now what do I do? Where do I go next? Because for whatever reason, I have to make those two arcs equal to where whatever time value, because what the hell did we just do? We took this bigger arc, found out its derivatives, where there's a time value, so we could solve for t. So let's just do that. Let's just take this first arc, and we're going to solve for the time value. So this just becomes t negative 4.9 t plus v initial sine theta, and that's equal to 0. So this has to equal 0, that has to equal 0. We're going to have negative 4.9 t over here, and then you're going to take this vi sine theta and divide by 4.9. So cool. So t, prime is going to equal, like this arc length to there, is going to equal V initial sine theta divided by 4.9. Isn't that really close what we get? Sure. So, I mean, just by similarity, T double prime is going to be equal, or our V initial is divided by 2, so we're going to have V initial sine theta divided by 2 times 4.9. And isn't that what we would get? Yep, we would get, you know what I mean? Hey, we're going to have negative 4.9 t plus 1/2 v initial sine theta multiplied by t. This has to be 0, so this either 0 or this whole product has to be 0. Bring the 4.9 t to the other side, and then divide this by 4.9. Alright, so I think that's a check on reality, and so here is our time 2. And I did get to here. I at least got to here, and I was just like, cool, but these 2 times don't equal the other time. That's the first thing I did, and I was like, nah, I don't know how to do this problem, and then I just gave up. And at that point, like, what do? If you can't figure out the next place to go for the axioms, you know, that's why I went to Excel. And just spending 2 to 3 hours in Excel is way more useful for our intuitive understanding of this problem. But now what? Oh, yeah, because just like this, what the hell did I even do for the first one? I found the time, cool, found it, but then I said time times the velocity in the x had to equal d. So then I can have just real simple equations that for this second one, t prime to get to here times the velocity in the x, and I'll say vx prime has to equal, OA. And then I'm going to say, I'm just going to call this distance A and this distance B, because else it's going to drive me nuts. So there you go. So you got A, and now we have t double prime times velocity in x double prime has to equal to that length. Okay, hell yeah. And I think that's it. I think that is the continuity. You know what I mean? That was the next place that I just couldn't figure out how to go. I was making, simple assumption errors, and then so we went to Excel. That's the whole learning process. And I don't see the full light at the end of the tunnel, but it's just like, oh hell yeah! Like at least we have more things that we can do that are logically and mathematically, accurate to what we're trying to get at. So what we just found t prime, and we have t double prime. So let's do this one. So we have, and where's our equation for d? You know what I mean? Cool. D is this thing. So now let's go t prime, v initial, sine theta, divided by 4.9, multiplied by vx prime. So we're going to multiply by v initial cosine theta. All right, hell yeah, and that's just a. And I'm obviously the v's are squared, but I'm not going to write it again. So now by logic, I can just really get to this one. I'll probably make a mistake, but no. So here's your t, and then your vx double prime is this, because your velocities in the x direction are always constant. So vx double prime is that. But I'm just going to write it like this. So we have that time sine theta divided by 2, 4.9, and we're going to multiply it by vx double prime. 1/2 v initial cosine theta. Cool. Hell yeah. And now we know from continuity that a plus b has to equal d. And that's it. That's the magic trick. You know what I mean? Every physics problem is usually comes down to like some sort of continuity. You know what I mean? It's just like, well, there you go. And yeah. And so cool. Well, let's do that. So we have a plus b. Now we can kind of simplify these. So we have v initial squared sine theta cosine theta divided by 4.9 plus this. This is v initial squared sine theta cosine theta divided by 4 times 4.9 is equal to D, V initial squared, sine 45 cosine 45 divided by 4.9. Alright, hell yeah. And, like, oh yeah, we can solve this pretty much straight up pretty easily, I think. I can just cross out the 4.9s, kind of factor those out. Cool. But yeah, that's about it. You know what I mean? This is sine theta cosine theta, and this is sine theta cosine theta. This is 1/4. You know what I mean? This is 1/4. This is 4/4. You know what I mean? I shouldn't have done the parentheses. But now we're going to have 5/4. You know what I mean? And isn't it nice to have that relationship? You're like, don't you remember how this was like 4 times the distance of this? And this was like, you know, if we divvied this up into 125, this would be 25, and this would be 25, 25, 25, 25, and then 25. 125. So, and we're kind of seeing that work out in the math. You know what I mean? We have 4 divided by 4 plus 1 over 4. So now we have 5/4. So we're going to get 5/4 V initial squared sine theta cosine theta is equal to V initial and why couldn't we have just factored out the V initial squared? I think we can. I'm going to leave it for one more time. But sine 45 cosine 45. Yeah, because I remember doing it. I just didn't get. I didn't get this right. I think what I did was just say, yeah, the mistake that I make. I just thought t prime plus t double prime was equal to time. I thought the time to go from here to here plus the time from there was going to be equal to, but that's obviously like horrendously wrong, just because the problem says, hey, if you do a double bounce, this will be a faster time. Alright, hell yeah, so we got that. But yeah, you can just factor out the v squared. And now we'll just get something in terms of theta. So now we have 5/4 sine theta cosine theta. And the crazy thing, this problem was only like blue. You know, it was intermediate. It wasn't red. But man, it thumped my brain, that's for sure. You know, it stumped me for almost like 2 days. Where you're just like, nah, I'm just gonna not think. You know, you by osmosis, see if I can come back to it. But that's where that, in Excel, that was the game changer. And this totally shows the learning process. Alright, so we have sine 45 cosine 45. And now we need to get sine and cosine. I'm going to pause the video and see if I can get any sort of relationship sine theta cosine theta. You know what I mean? Is there a way to just get it as a function of like, I don't know, like 1 minus cosine squared theta? That's what I'm thinking, that because this is very similar to sine squared theta or cosine squared theta, and we know that 1 squared is equal to sine squared theta plus cosine squared theta. So, you know, if we thought this was sine squared theta, you know what I mean? Well, that would be 1 minus cosine squared theta. You know what I mean? So, and just, you know, I'm just going over like where I'm at in trigonomic identities. But I at least can identify that. If you have two things multiplied together, sine and cosine, well, if it is just sine squared, cool. You could replace sine squared with 1 minus cosine squared. You can always do that if that helps. Probably doesn't help, but you can do that. And so that's very similar to what we have here. You know what I mean? If you have cosine squared theta, well, that's going to be 1 minus sine squared theta. So maybe, you know what I mean, maybe there's a relationship that this is 1 plus, you know what I mean, cosine squared theta. Maybe it's 1 plus, you know what I mean, cosine squared 2, you know, angle 2 theta. I don't know. It could be something fun that we'll learn. I don't know if there's any way, but the reason that we want to get there is because then we can have an equation that's just like, hey, you know, inverse cosine. Theta is inverse cosine, you know, all that jazz. And that's what we want. So I'm going to pause the video, catch on the flip side. Alright, hell yeah. We're back, and man, this book is sweet. I kind of picked it up with a bunch of textbooks for real cheap at a garage sale. It was amazing. $1 a textbook. This guy was just like, nah, I'm done with my books. And so, but yeah, this is the handbook. No, this was from a family friend, actually. Handbook of Engineering Fundamentals. They knew I was kind of, doing problems and stuff, so I actually inherited this. But I think it's only like 20 bucks used, on YouTube. Or on, kind of the online Amazon stuff. But, you know what I mean? Just for just an all-encompassing book, like, I enjoy having it. Maybe just for these first sections. I mean, once you get into it, it's kind of just more like all types of engineering. But, I mean, you got fluid stuff. But I'm just interested in kind of the math, you know what I mean? Math, tables, logarithms, and then definitely trigonometry. I guess that's all I'm going for this one. I was just satisfied that it has a pretty decent trigonometry section. So yeah, look at all that. And cool. So we found the relationship. I kind of even lost my page, but hell yeah. So if we do have sine theta, cosine theta, well, 2 times that is equal to sine 2 theta. You know what I mean? Cool. So now this is very helpful, but we do have to get it into this form. So we'll take this and we'll go 1/2 sine 2 theta is equal to sine theta cosine theta. So now we have sine theta cosine theta, and then we're going to get, so we can just substitute straight up right in there for this. And then we're going to have 5/4 times 1/2 sine 2 theta is equal to sine 45 cosine 45. Heck yes. And so now we want to find this angle theta. Let's bring this stuff to the other side. And we really can't simplify too much. This goes to 5/8. So when we multiply it over here, this will be 8/5. So okay, so now we're going to have sine 2 theta is equal to 8/5 sine 45 cosine 45. Now to inverse this, you know what I mean, we're going to get something that's 2 theta is equal to inverse sine 8/5 sine 45 cosine 45. Okay, but now we just want theta. So theta is going to be, so we got to divide by 2. 1/2 inverse sine 8/5 sine 45 cosine 45. And this looks sweet as, so it has to be right. So mode, we're in degrees, 0.5 inverse sine 8/5 sine 45 cosine 45. And we're money. Hell yeah, we get the answer in the back of the book. I got an endorphin rush right now. You know what I mean? That's what we live for. And then when you can't do a problem, you're just like, nah, I throw in the towel. I threw in the towel 2 days on this one. It was just like, no way is this going to stump me. But then I'm just like, hey, let's turn it into a learning video. Even if it's like a 5-hour long video, who cares? Because my style now is going to be like, hey, we're just going to give you the answer at the beginning. Because no one's got 5 hours. I can't even watch my videos again. But I do watch just a little bit if I'm intrigued, just to see if I'm making, if I said this was, tangent 45, sine 45. Obviously that would just be wrong. So some things I'll say wrong, and that drives me crazy. You know what I mean? V initial cubed, sine theta, cosine theta. V initial cubed. You're just like, holy Toledo. You would never. There's so many little errors like that I would make. Okay. Anyway, we got the angle, and it was 26.6 degrees, and now we can answer that question because what was the initial time for that first one? Let's get these. Based on doing that, taking the derivatives and integrating, getting the position equation, solving for time when the position was 0. You know what I mean? That's why this position equation is an x squared, because you have a position 0 right there, and this equation covers both those. You know what I mean? And it knows that we're going in that direction because it has this component of that initial velocity in the upward direction. You know what I mean? So it's perfect. And so that's what we did, and we solved for t. Where's our first t? T was this. So we have T is V initial sine 45 divided by 4.9. And then we'll have T prime. That's going to be V initial sine theta 4.9. And we can just kind of mimic these. But we know that this one is going to be V initial sine theta divided by 2 4.9. Because that indicates that the velocity was half. You know what I mean? So don't just copy paste. Anytime you copy paste, you know, it's like, am I visually understanding what's going on? Because now what they want to know, what's the ratio between the time, because it's obviously going to be lower. So this is T prime, T double prime. This is T prime. So the time it takes for the ball to do the one bounce will be T prime plus T double prime. Cool. And they want to know the ratio between that and T. I'm sorry, this is just T. So cool. So we're going to do that. And if we did it in a ratio, because you know we kind of want to do it legit style, we're going to go this plus this. So we're going to have V initial. What the hell are we adding? I mean, isn't it just this straightforward? If you add this is 1/2 and this is 2/2. So we're going to have 3/2. So there you go. 3/2 V initial sine theta. And now we're going to divide by this, which is V initial sine 45. Oh, and you know, this was a factor of 4.9. The 4.9s disappear all around. And even the V initials. So cool. We're just going to have a ratio of 3 sine theta divided by 2 sine 45. And is that what we get? We're going to store this as theta, and we get 3 sine theta divided by sine 45. No. 2, I'm sorry. 3 sine theta, I just wrote it kind of bizarre, divided by 2 sine 45. And yeah, we get that ratio of 0.949. That's the answer in the back of the book. Got my second endorphin high. And we can kind of simplify this. This will be 3 halves. I don't know, just make it look better. I don't know what we should do. Sine theta, sine 45. That's the ratio. The time for, you know what I mean? 2 bounces compared to the time for no bounces. I think that's a pretty good indication. Now the only other thing that I want to do is look at this. The angle, shoot. Like, okay. This problem is also fairly interesting. It's like, let's say you're a first baseman and you always want the ball to be like right on the ground, you know, and you're scooping it up, you know what I mean? Because that you want one bounce, but you want that ball to not bounce a second time, you know what I mean? And you don't want it like sweeping up like here and then bouncing kind of real high into the first baseman's glove. You just want every 2 bounce. So I'm going to watch this because I tried to be a first baseman when our team was like the winning team, and I was the worst player on that team. And that caused severe trauma, being the worst player. And they're like, what position do you want to play? And I was like, well, I used to play first baseman on my the team that I wasn't very good on last year. And they're just like, no, you can play, I couldn't even play right field because that position was already taken. And so I would substitute into right field probably. But then they're like, well, they kind of halfway through the season, they were always winning every game. So they're like, well, you know, this team, we're totally going to crush. So they threw me in as first baseman. And holy Toledo, I wasn't prepared. You have to, like the guy who actually played first baseman on our team, he had a glove that was huge. And my glove was really tiny. It was like kind of like that Sandlot glove. And so, oh my God, then they would do this. They would throw the ball just like in the MLB, where I would have to constantly do 1-hops that would probably, you know, were aiming right at my face if I didn't get the glove in the right place at the right time. It was awful, you know what I mean? But yeah, that's okay. End of story. But yeah, so you want to hit that 1-hop right at the dirt, and that's why being a first baseman is got to be the hardest position in any professional sport. I mean, holy Toledo. You know, I mean, good luck with that, first baseman. But yeah, you just got to... Alright, hell yeah, my camera cut out, but we're done with that story. And what I want to go back to is, you know what I mean, let's get this equation all in letters. You know what I mean? Hey, this is a 45-degree angle that we're comparing it to. That's our initial angle, and that makes sense. If you're an outfielder, you can get the ball the farthest distance by throwing at a 45. But from this problem, it says, well, that's going to be the slowest. But the other part of this problem that's very fascinating is that once it does bounce, they're saying your velocity does reduce by half. And so where the hell is that in this equation? Well, it's probably buried somewhere in this 5/8. It's not in this 1/2. You know, it's really tempting to be like, whoa, isn't it just right there? No, that was just a function of 1/2 sine 2 theta was equal to that. But everything before that was combining these. So what we were trying to find out was the ratio between the times. And so we can go back and say, hey, t double prime, this one is the velocity times a constant. I'm just going to say k. And I'm going to say k is the reduction of speed. You know what I mean? That makes sense. So if k is 1, there is no. You know what I mean? It's going to bounce perfectly elastic and then continue with the same velocity that it impacted with. You know, kind of like a pool ball. And then if k is 0.5, you know what I mean? Then we have our scenario. So this t1 double prime can become k v initial sine theta divided by 4.9. And so now when we're adding these up, we're going to have this. This doesn't become 2 divided by 2. This doesn't become 1 divided by 2. This is k. So now when we do this is going to be 1 plus k v initial sine theta divided by 4.9. So this happens all the time. You have, you know what I mean? Hey, we have the same. Look at all this. v1 sine theta 45, v1 sine theta 45. But now we have something multiplied by this, like some sort of variable. And so how do we add these two terms? Well, it's just going to be simple addition, but you're going to factor out this. So basically, you would add those together, but then outside of that, you would factor out v1 sine theta 45. That's what we do here. That's why this is kind of factored out. And then it's just 1 plus. The only thing that's left is the 1 plus k. So there's two ways to visualize that, or you can just see that, hey, 1 plus k, I'm going to factor that out, and then I'm going to be left with, I don't know. But anyway, so there is the equation for time 1 t prime plus, you know, I mean, the first path and then the second hop. That is the time for that. So now the ratio is just 1 plus k v initial sine theta divided by 4.9. And then we're going to divide that by t, which is v initial sine 45 4.9. 4.9's cancel. V initial it's not a function of v initial, and so this ratio is t double prime t, and so now we're going to have t double prime t is equal to 1 plus the constant. You know, the constant is the reduction in speed, sine theta. I'm just going to say theta prime. You know, it's like what is the angle to do the two bounce thing, divided by sine theta naught. Cool. So our initial theta. So now we have a lettered equation of the ratio of the time savings, and so now if oh, check this out. If there is, I was wigging myself out, but if it is elastic like pool balls, there is no reduction in k. K is 1. K is 1 for that scenario, so this becomes 2. So then your ratio, you can increase the now is that the way that this problem is designed? I feel like this number shouldn't. Oh, this is a bummer though. Holy Toledo. Because, okay, because this theta prime is now this. This is theta prime. You know what I mean? This is the angle that we're trying to find. And so once we found the angle, sure, you can throw it into there. So let's kind of grab a new sheet of paper. So we have theta prime. I'm going to write this one down. Is 1/2 inverse sine 8/5 sine 45 cosine 45. And then once we know that, we know t double prime divided by t. And this is t prime plus t double prime. Sure, that's the ratio. This is going to be 1 plus k sine theta prime divided by sine theta naught. Okay, so now we can throw this into there, and we can get t prime plus t double prime divided by t is 1 plus k sine of the angle. Yeah, and this gets hella complex because now you got to throw in that whole thing, and it's, yeah, I don't know. You know what I mean? Yep. I mean, you could say, now let's just do it. I don't want to make any mistakes on this. So that's theta prime and that's theta, even though this is like 2 times the angle. 2 times the angle is that, but let's do it. So we have sine of 1/2 inverse sine 8/5 sine 45 cosine 45. So sure, there might be ways to simplify stuff, but you know, who cares? You know, that's a fully accurate representation, and now we have sine theta naught. So now this is a function where if we throw in, so right now we only have the one parameter, and this is theta naught right here. So this still doesn't tell us anything. It's still just a function of the slowdown. But what we want to do is go back to, you know, our continuity. I think that's a good place to go. Is a plus b is equal to d. So we can say, hey, a is going to be v initial. Well, let's just talk this through. This is going to be theta naught. This is theta. This is theta prime. This is the angle that does the double bounce to go the same distance. Right here, this has to be the 1 over 2. So we're going to do 2 right here, and then multiply by k. So that's what this is. So that's useful because what we're trying to do is get this equation as a function of k and theta naught. Because, yeah, right in here, there was a k of 0.5 that we need to, so let's do it. I think we got it. So now we're going to do a plus b equals to d, and I'm going to do 2 steps at once. We know if we do a plus b is equal to d, there's a v squared in everything and a 4/9 in everything. So we can just really simplify this. A is sine theta prime cosine theta prime. That's it. Plus, and this is going to be k sine theta prime cosine theta prime. And you know, we can, because we're factoring out the 4/9, or, you know, the acceleration, factoring out the initial velocity squareds, and we still have this still has a 2 underneath it, so this is still divided by 2, but now we'll have equals to sine theta naught cosine theta naught. That's the 45. All right, and so now right here, same thing. This is going to be 1 plus k divided by 2 sine theta naught cosine theta naught. Cool, because we kind of just foiled it through, and it's sine theta naught cosine theta naught. All right, heck yeah. And the whole thing that we're trying to get at is trying to find the ratio as a, no, we're trying to find the angle. You know what I mean? Hey, what angle do we do with an input of the velocity reduction? You know what I mean? If you have a velocity gun, this is very interesting. Even in MLB, if you were trying to dial in players at like the physics level, you know, you would go to the field surface and be like, well, is your ball going to hit the dirt and then bounce to home plate? Or is it going to hit the green and the grass and then have a slower bounce? You know what I mean? And you have speed guns out there, so you could figure out, you know, just with any throw, what the incoming velocity is compared to the outgoing velocity. Or you could just take some video and kind of figure that out as well, just to see what the reduction in speed is. Like I could even do that with a GoPro. And some you know, tape measure, and then throw some balls and stuff. Okay, so we do have this relationship. We do know that sine. This is going to be, yeah. What's our equation? We have 1/2. I mean, essentially, sine 2 theta is equal to 2 sine theta cosine theta. So we'll have 1/2 sine 2 theta is equal to sine theta cosine theta. Well, what do we have? We have sine theta cosine theta. Nice. And so, cool, we're going to go 1 plus k divided by 2. And we're going to go 1/2 sine 2 theta prime is equal to sine, and even over here I can just do sine 45 cosine 45, and we can you know, in the end we can figure that out, because a lot of people are just like, oh, take your letters all the way to the end. Hell no, the letters get so confusing. You know what I mean? Just the fact that you're doing little symbols, one symbol means one thing and another. This 45 is super obvious that, hell yeah, that's the initial velocity that we're throwing in, and that's what we're comparing to the theta naught of, like, hey, this lower velocity. Okay, so we can factor this maybe 2 through, so we can get 1/2 plus k divided by 4, and then we'll have sine 2 theta prime is equal to that. So we're just going to go sine 45 cosine 45 divided by this, 1/2 plus k divided by 4, and then we're going to go inverse sine that. And then, so then we get 2 theta, and then we got theta prime is 1/2 that. So cool. So theta prime is 1/2 inverse sine 40, yeah, we'll do it, sine 45 cosine 45, 1/2 plus k 4, and then, you know what I mean? So heck yeah. So here would be my equation. Theta prime, the angle that you would want to throw to do a perfect double bounce would be 1/2 inverse sine sine theta naught cosine theta naught divided by 1/2 plus k divided by 4. But holy Toledo, if this is sine theta naught cosine theta naught, and we know that's just 1/2 sine 2 theta, why the hell not just do that? So cool. So we're gonna, right here we're gonna have 1/2 sine 2 theta naught, and then the 2 is gonna go downstairs, so we're gonna have a 2 down here, and then hell yeah, that 2 is gonna cancel with that 2, so we're gonna have 1. Now we're back to 1 plus k divided by 2. So that's helpful. And now we'll go over here. Theta naught is equal to 1/2 inverse sine 1/2 sine 2 theta naught divided by 1 plus k divided by 2. And there you go. And you know, for the life of me, I don't even know, you know, but now we have a check on reality. If we made any mistakes, we can find them. You know what I mean? That's why this stuff, you wouldn't want to run start to finish, because you're just going to make an error somewhere. So hell yeah. So we got 0.5 sine 2 times 45. Yeah, and what's 2 times 45? That's just 1/2. So at the end of the day, we'll have 1/2 divided by k would be 1/2. So we would have 1/4. 1 plus 1/4. That's where we get that 5/4. Cool. So you got 5/4 downstairs, and then you'll have 1/2 upstairs. So you're gonna have 1/2 times 4/5, and there you go. There's that. Oh, and did I make a huge mistake that this is... No. I think I'm good. But yeah, let's run through this. This sine of 45 is 1. You're going to have 1/2 divided by 1 plus, this is going to be 1/4. And then so this is going to be 4 divided by 4 plus 1 divided by 4 is 5/4. And then 1/2 divided by 5/4, same thing as 1/2 divided by 4/5. And yeah, you get 4/10. Cool. Alright, that's what I get. So this for our problem would be 4/10. Yeah, 4 divided by 10. And inverse sine of 4/10 is 23.5 times 0.5. No, hell no. So we made an error somewhere. Let's see. Yeah, we're in degrees, so we got 0.5 sine 2 times 45 divided by 1 plus 0.5 divided by 2. Yeah, inverse sine of that times 0.5 is hella not what we want. Okay, so we need to go back and see potentially where our error is. And hell yeah, isn't that what we love? You know what I mean? Man. Yeah, that sucks. I feel like I'm missing a sheet of paper. It's like, how the hell did we get here? Didn't we have this? And we said A, B, D. And was I even wrong on this? You know what I mean? It's like, do I need to go back to actually where the hell that came from? So yeah, this B term is going to be the second hop. That is going to be the position in the y of the second hop, which is going to be negative 4.9. So we got negative 4.9 t plus k v1 sine theta t. And from that, we can figure out that the t double prime will be, you know what I mean, k vi sine theta divided by 4.5. So I'm going to say t double prime is k v initial sine theta divided by 4.9. And then I'm going to say the distance, because this, what we found is that this is the time, and then the velocity this direction is constant. And the velocity on that is going to be k v initial cosine theta. So we have k v initial cosine theta times k v initial, perfect. So it's a k squared. Hell yeah. I'm glad we did this. You know what I mean? That's where our error was, and we found it, and now we're just happy as a clam. And so now we get k squared, v initial squared, cosine sine divided by 4.9. This is t naught squared, and so that's where we ran into our error right here. So this is k squared, and then when we go for our distance, so this is k squared. So a plus b. So hell yeah, and you know, even we did that too fast. A plus b is equal to d. Where did we even do that fast? We said, hey, no 4.9s, no v squareds. So now we're going to have, so anywhere where there's a k, where's the first time we actually did that? I think, yeah, we did too many steps at once. So, Alright, heck yeah. So I think I can do this. A plus B, hey, is sine theta cosine theta. You know what I mean? And but we have 1 is 1, you know what I mean? And this is k squared. So we're going to have 1 plus k squared sine theta cosine theta, that's a plus b, is going to be equal to d, which is just sine 45 cosine 45. So wherever this looks the same, yeah, is it on the new sheet of paper? Probably right here. So, okay, what did we just write down? 1 plus k squared. And I guess let's just run with this. So this is 1 plus k squared sine theta cosine theta sine 45. Holy Toledo. Why would this be k divided by 2? Oh, well, is it just k squared? Yes, because this was, oh man. Is that why this was 4? You know what I mean? Yeah, this was 4. Okay, perfect. Yeah, this was 4 because it was k squared. K squared is 1/2 squared, which is 1/4. That's why we had a 1/4 on that term. And that's why anywhere now that I see the mistake of k divided by 2, well, hell no. That's just k squared. And so, so perfect. So now I can just quickly probably get to... And I don't know which sheet of paper came first. I mean, didn't we get to here? So we have theta prime is equal to 1/2 inverse sine 1/2 sine 2 theta naught 1 plus k squared. So let's do that. So now we'll have, see, pull this up again. I'm just going to do it one step at a time. So we have sine 2 times 45. Obviously it's 1, so we have 1/2 divided by 1 plus 0.5 squared. Holy hell, that's still 0.4. Inverse sine of 0.4. No way. Man, it's yeah, you know, having little hiccups are so crazy because you're just like, yeah, they're almost impossible to, holy Toledo. But I do want to do this one, you know what I mean? So I'm going to go back to the position equations and just kind of run through it all, because that is good for my intuitive development of this problem. Position equation for y is this. So if we solve for t, we're going to get, whoops, get some more light. Alright, so if we solve for t on this, one of these t, this goes to t, so we need to take this divided by 4.9. Got it. So v initial sine 45 divided by 4.9. That is going to be our t. And then for our first top, it's basically the same. V initial sine, you know, theta naught divided by 4.9. And then this one's going to be different. It's going to be k, you know what I mean, k v initial sine theta naught divided by 2. Alright, sweet. Now the velocity, so that's the time. Time already is a function of k. You know what I mean? Because, so that's where k shows up twice, is because if we do the distance of b, well, it's going to be t prime, no, b is going to be, it's going to be k times k. So now we'll have k squared v squared cosine sine, you know what I mean, and these are the knots. And then for this one, it's not. So if we added those together, it's going to be 1 plus k squared, and we get that term. And then so the distance between a and b is 1 plus k squared sine theta cosine theta. You know, sine theta cosine theta, and that has to equal the other side, which is v initial sine 45 divided by 4.9. And that's where we got, hey, we can factor out the 4.9s on both sides and the v squareds on both sides. And I'm sorry, D is v squared sine 45 cosine 45 divided by 4.9. So the v squareds cancel. And then we get a continuity between, let me just write this, sine theta cosine theta not plus k squared sine theta cosine theta naught is equal to just sine 45 cosine 45. So that's the relationship that we get. This is going to be 1 plus k squared. So then we can bring that downstairs over here. 1 plus k squared. And so this is going to equal sine theta naught cosine theta naught. Now, going back to the, if this answer times 2, no. All right. So now from here, we need to solve for theta. And we can go back to our equation that sine 2 times the angle is 2 times sine theta cosine theta. So right here we don't have 2 times sine theta, we just have 1. So this becomes 1/2 sine 2 theta naught. And this becomes, I think that's where the error was. Okay, I found my error. Like right here, like if we're changing this into this form, it's no longer theta naught anymore. We have 1/2 sine 2 theta naught, where no, and this theta naught is no longer theta naught. This is theta asterisk. Holy Toledo, holy hell! But that was this. I knew that was gonna get me. Anytime you're doing like half angle things, well, this term is this term for what we want it to do is 45. You know what I mean? But 2 times what is 45? Well, it's going to be 22.5. So 2 times 22.5 is 45. So hell yeah. So that's why we do these, because like I'm just learning kind of what mistakes you can make, and then kind of learning on the fly. All right. So yeah, that was the huge mistake. So now our input, if we're going to use this equation now, we can modify this equation later, but if we're going to do this, yeah, holy Toledo, does that even make sense? So if we have 2 sine theta cosine theta, that's equal to, well, let's look at the identity. I got to look at this. So if we do have sine 45 times cosine 45, no, because I think what I just said was absolutely wrong anyway. And now we're going to have sine of 90. No. See, I did it wrong. So, oh, no. This was 2 times sine 45. Sure. So, yeah. So 1/2 sine 2 theta is equal to sine theta cosine theta. Is that what they're saying? Yeah, because sine theta cosine theta is 1/2, and sine 2 times 45 is 1/2. Okay, so no. Everything I said, I just misspoke, and I just I'm trying to exactly. Again, when you have an error, you're just trying to shove things, into it, and you might make bad assumptions. And so, okay, so hopefully we're back on track. This isn't an asterisk. This is 45. And so we have this becomes 1, and then you have 1 plus k squared. Alpha k, 0.5 is stored as alpha k. 1 plus k squared is 1.25. 1/2 0.5 divided by that is 0.4. And then so we're going to have 0.4 sine 2 theta is equal to 1/2 sine 2 theta naught. And now we're going to multiply by 2 to get 0.8. Yeah, no. So I don't know where I made my errors before, but yeah, this should be going pretty good now. So we'll have 0.8 sine 2 theta is equal to sine 2 theta naught. We want to solve for this, so we'll go inverse sine of this is equal to 2 theta, and then theta naught is 1/2. So now we got what? Sine 2 times 45. That's 1, but now we'll have inverse sine of 0.8 and then divide by 2. Hell yeah, then you get our answer of 26.6. So it was right here that I wasn't multiplying by 2. So if we go back, can I actually spot that error now? Yeah, like right here. Yeah, because right here was wrong. So that's fascinating to like. So yeah, well, let's take this to a legit form. So we have 1/2 sine 2 theta naught divided by 1 plus k squared is equal to 1/2 sine 2 theta prime. So I think I know what I did when I if I ever turned this into this. No, we got the 1/2 there. Alright, well, let's carry this one through and see what the difference would be. So this is what we want right there. This is all given. This is 1/2. This is 1/2. So those can just drop. So now we have, and now we're going to take the inverse sine of this, and we're going to be left with 2 theta. And then we'll have to take 1/2. So we'll have 1/2 inverse sine of sine 2 theta naught 1 plus k squared. And hopefully it's different than this error. So this is 1/2 sine inverse sine. Yeah, so this 1/2 is no longer there. Yeah, so that 1/2 was the error, and that isn't there. Because it, yep. So yeah, there was a mistake. That was the mistake, and I can't even, begin to see where I made it in this. I don't even want to. But yeah, this is the whole point. We got our equation for theta naught. So this is the angle that you'd want to throw the ball is 1/2 inverse sine 2 theta naught divided by 1 plus k squared. Cool. And so what this says is whatever input angle you're trying to match, I can have an angle that will get there with one hop. That's what this says. You know what I mean? Regardless, or whatever that word is, irregardless of whether it's faster, it's obviously going to be faster. But what this says is like, hey, if you threw that, I can throw this and get there the same distance. I can physically get there in 2 hops. This is a 2-hop equation, and And just in the wash, it says I can get there faster. I will always be faster. So if you throw at an angle like this, really shallow, I can throw at an angle like this, and I will get there faster, and my second hop will land right where your first ball landed. So this is the 2-hop equation. Its input parameters are, hey, what angle did you throw? When my ball does hop, what's its reduction in speed? You know what I mean? K is just either, it's not a reduction in speed. It's like, hey, if I have an initial speed of v, my next speed after the bump is going to be kv. So, you know what I mean? Maybe it's half v. You know what I mean? So that's where this constant. This is going to either be a very low number to either 0. Yeah, because if the ball sticks right there, you know what I mean? What are you going to do? And yeah, if the ball stops where it lands, you can't do the 2-hop problem, and this should work itself out. That's the cool thing about axioms and equations. If I do throw in 0 for k, my angle should just be 45. And can I even see that? So we're going to have sine 2 times 45. This is just 1. 1 divided by 1. And then inverse sine of 1 is 90, and then half of that's 45. So cool. And inverse sine, I'll just do it. Inverse sine of 1, 90. So cool. Now we have a practical application of what the equation is. And I just don't think you can get that without doing like the whole Excel or figuring it out. Maybe you can. Maybe these numbers are just like, you know, you're just popping out of the page at you. But definitely not for me. And so that was the one equation that we got. And then the other equation was, I think it's this equation. And so there you go. So those are the two equations. I'm going to run this equation once in my calculator just to make sure it works. So we got 1 plus 0.5 times sine of, oh, is my theta in here? Yeah. So we're going to go sine theta times 1 plus 0.5 divided by sine 45. Cool, and yes, so these are the two equations. So hell yeah. So now I can make the video from the start forward. I'm going to, might as well. I mean, why spend 4 hours on something and then not show you the 5-minute solution? And I think it makes sense to do it that way, because then if you really want to see how I learned it, that is my learning process. It sucks. You know what I mean? It is trial and error. It is making little mistakes, but that is the best. Is like, can you make a mistake and then go spot it? You know what I mean? You should do purposefully make mistakes. Get into bad habits purposefully, and then see what errors those bad habits causes. And then it's like, hey, then you have little wake-up moments like, no, I don't want to make those bad habits again.